Okay, good morning, everybody. It's my pleasure to be the moderator today for Toki's PhD defense on his thesis Bufferbloat and Beyond, Removing Performance Barriers in Real-World Networks. And first of all, I want to introduce the important persons that visited us today. So, yeah, besides Toki and his family and friends, where we are very happy to have so many visitors, especially from Denmark today. We have the committee and the opponent. So first, the opponent is Dr. Luca Muscariello from Cisco Systems from the United States. So thank you very much for the long... From France, okay. Then it was one here. Yeah? Okay. Okay, then from France. Thank you. And then we have the members of the examination committee. And then next is Gunnar Karlsson from the KTH, Royal Institute of Technologies in Stockholm. Then we have Professor at KTH. Then we have Principal Investigator Marco Kojo from University of Helsinki in Finland. And we have finally Professor Michael Belzes from the University of Oslo. And the supervisor is Anna Rundström, and co-supervisor is Claire. And then we have also the supplement examination committee, which is Justin Anderson. Yes, so the procedure is as follows. So in the beginning, Toke will present his thesis for about 30 minutes. Then we will have a break of 5 minutes and we'll rearrange the settings. Then we have the opposition, which takes some time, and then afterwards the examination committee and supplement examination committee members are welcome to ask questions, and then the broad audience can also come in for the discussion. Yes, before we start, usually the candidate can also tell whether he has anything to announce. Typically, there might be some minor mistakes.
I get that, but I think actually Luca agreed to start.
Okay, so Luca will.
Okay,
so Luca will start with the presentation and then introduction. Okay, so that's it. So we do it a bit different today, but that is more the traditional Swedish way. Yeah? Okay, good. Okay, good. So very good. Then we do it this way, and then we will start with the presentation. And we have live streaming, so if anybody doesn't want to appear, please tell me in the break. And then the camera will not be targeted.
All right. Okay, so this is a very short introduction, essentially to trying to give a historical perspective of what Toki has done in the last 3 years. And there's a lot, actually. Toki's work is about, as he writes in the manuscript, removing performance barriers. What is this all about? So removing performance barriers assumes a sort of optimality concept, like you are trying to optimize applications, networks, latency, and other performance measures. But essentially, behind all that, and all the mechanisms and protocols and algorithms you design, you implement, and you deploy, there is behind all that, there is an optimality principle. So you are starting from the very beginning, thinking about how to optimize some of the objectives you believe are important for the network, applications, and ultimately the user. So I'm gonna go through a timeline that you really chosen my case, of course. Starting from the 80s, from some of the work that has been done in the MIT from Robert Gallagher and students. So this one of the first paper on optimizing congestion control in the internet, very early work. It was actually a follow-up work of some of the first optimization, network optimization work made between MIT and UCLA. talking about seconds and Leonard Kleinrock. And this was in the late 70s, and this was one of the first work to focus on congestion control. Then you have to wait quite a lot in the PhD implementation. Just an email in the TCP list from Dan Jacobson talking about an algorithm to adapt the amount of traffic that is sent throughout the network. It was just a very long, you can see there, long message. It was actually a long paper written in email. And then actually a few months later, this appeared as a full paper at Cisco describing essentially downwards push directly in the paper. And this was actually the beginning of TCP congestion control. And still, there's a lot of Dan Jacobson in this timeline, but right after, a few years later, additional optimization mechanism to essentially optimize congestion control and traffic flowing into the network. Well, we started having also additional work on how to manage the queues and forwarding policies into the internet. And this was an early work by self-employed person that appeared, and this is actually something that was widely deployed in the internet. Like random Red was essentially deployed everywhere, never used but deployed everywhere. Like every single router and Red implementation to optimize congestion control in the network. And then stay there for a very long time. So anyone had to add one Red implementation in every single box. Now then we have to wait quite a lot to in the late 90s to get a very important work again about network optimization from Frank Kelly. This is a very important paper that everyone should know, or at least every networking professional should know. Because this is essentially there's a link between this first paper, the first paper, and this last one about essentially stability. Like, yeah, you try to optimize the network, but at the end of the day, you need distributed algorithm to do it. And so you have this concept of optimizing with distributed algorithms that can stabilize autonomously. And this is TCP essentially. And the scale, and it was actually the first proof to say, okay, what we're doing with TCP is right. But there's a more general set of models to do that, and this was the foundation of that in the late 90s. In parallel, there's another timeline. So of course, late 90s to today, there's a lot of time passed, and a huge amount of literature out of those fundamental works, and work of also for many people here. But there's another parallel timeline. So Kleinrock here is on top of the list. And this was a book from Kleinrock that was the foundation of essentially using mathematical models to predict the performance of queuing systems. And it's used also even today. It's used. I have it in my office, and it was essentially a different perspective with respect to the other timeline, because in this timeline you have essentially you have for the first time the concept of stochastic workload. Like the network is not just set once, and then you have sources and applications that are set at once and they communicate. You'll know that the network behaves in a very different way. You have an application that can be used in the network at any time, random time. And it's also, so the statistical properties of the workload is very important related to the performance of the network, but also the impact of that workload and performance to the way you design mechanism, protocols, algorithms. So you cannot just neglect the fact that the network as a stochastic workload is driving the traffic flowing through it. Now, I was mentioning this early work from John Nagel that was for the first time trying to essentially raise a little bit of discussion about fairness in the network. Like, okay, so we have all these mechanisms. What about fairness? Remember that this is 85, so it was much earlier than some of the work trying to formalize the concept of fairness in the network. So people started thinking about this, while maybe today it's taken for granted. And then we had additional work, again from Robert Gallagher at MIT, was another PhD thesis, Ellen Kenny, which was the first PhD thesis on thread queuing algorithms. Here, written as round robin scheduling for fair flow industry. So always same people coming back all the time, but there's a whole literature that actually came out of this preliminary work. And then we have to wait until the 90s for stochastic current skewing. And in fact, in the 90s, Paul McKenney, who was a first formalization of a mechanism that actually is implemented some of the concepts that presented in Ellen PhD thesis. Again, still preliminary. We have to wait several years to get a lot more in terms of defining the full problem as in terms of optimality under a stochastic problem. So this is a work in 99 in Robert Masoulier, was the best paper this year for many reasons. And then we have to wait until almost 20 years ago for the first paper on a comprehensive framework for quality of service by using flow environment work. Now, this is more or less a timeline that arrives until 20 years ago. And then there's been 20 years of research based on all these different frameworks. And we have to wait 20 years to get this. I use this milestone from Luca's work, which is the publication of an RFC early this year about one of the most recent mechanisms to address some of the optimization or the condition control and fairness in the network. And this is where I stop, and I let Toki continue.
Right, thank you very much, Luca. So, as we've heard, what we will be talking about now is Bufferbloat and beyond, different performance barriers in the real-world network. But as Simone alluded to, first I will show you this. So, writing a PhD is all about learning, and I've learned that it is possible to configure your LaTeX to randomly eat characters from your mathematical formulas, which of course is not so good. So there's a written errata sheet if you haven't already signed up. I'm not going to go through it. This is just all the stuff that needs to be fixed to get this to work. But moving on, what I'm going to talk about, I'm going to do a little bit of background on what is Bufferbloat, what is it that we will be talking about, what are these performance barriers that this is about, and then I have structured the presentation around the whole research questions. How bloated is the internet? Can we do something about this with queue management? Then we have Wi-Fi, and then we go beyond Bufferbloat to go really fast at ludicrous speeds. So we start out with what is this Bufferbloat and why is there an elephant on my thesis? As you can see, the white line here at the bottom is your network path where you send all the traffic. And you can see the elephant as this big lumbering, big download that you're downloading at once. It doesn't need to go anywhere in any particular speed. It's just going along. And it takes up, obviously, the whole road because it's an elephant and it's big. And then you have your two mice that want to go past it. These are the small flows of traffic you have through the internet, like your like button when you click on something on Facebook or a phone call or something that it's not very big, but it needs to go where it's going immediately. And of course, the elephant is blocking its path, which is not so good. So what can we do about this? Well, fortunately, we have the friendly penguin. This is Tux, the Linux penguin. It's the mascot of the Linux operating system, which I'll come back to. There's that platform I've been using to implement a lot of this stuff. And Tux is friendly and would like to help, so he will stand there and he will guide the mice off to different paths so they can go around the elephant instead of having to wait in line behind them. And so this is Bufferbloat is the big bloated elephant, and the queue management is the penguin that guides the mice around the elephant. Simplifying a little bit, but you get the idea. So Bufferbloat is an example of a performance barrier in the network. So as Luca mentioned, this is all about trying to get the network and the systems on the network to perform as good as they can. And of course, there's sometimes you run into
that way. No, other way. One more step. Now you're in camera.
Great. So now I can't see. Right, so you run into some barriers occasionally that will prevent this from performing optimally. Bufferbloat is one of them. We have the Wi-Fi performance anomaly as well, which is something that happens on Wi-Fi networks with lots of different stations. And then once we try to go to high-speed packet processing, we get some other performance barriers that we might run into. So this is sort of the overarching theme of the thesis. What are these performance barriers? How do we analyze them? How do we resolve them? And as I mentioned, we have the Linux Penguin featuring prominently in this work. And that's because Linux is an open source operating system that is widely available. It powers many of your routers at home, even though you may not know it. And it's easy to modify. You can actually implement it, and at the same time, it's a production-ready system, so you can actually get it deployed and get it to use. And so I have had this as a focus, trying to get the solutions to the point where they can actually be implemented in Linux. And there's only one of the papers that hasn't gotten in yet. All the other stuff is actually included in the option code. So. As I mentioned, I have 4 different research questions that have been driving the work of this thesis. How bloated is the internet? Can we do something about it with queue management? What happens when we try to send stuff over the airwaves on Wi-Fi? And what happens when we go beyond this to high-speed networks? So the first point is how bloated is the internet, where we try to answer the question, is this Bufferbloat thing where you have these queues that build up, is this actually something that happens in the real world? Is this in the internet as well and not just something you can show in a lab? And we did this measurement study where we tried to measure there's a big data set on this measurement labs platform that's run by, among others, Google, where we have like a few 100 million different traces of people who run speed tests. And what we saw was, we thought, okay, we have this data, what can we look at? And we looked at the difference between the minimum and the maximum round trip time. So in this whole data set, and we found that the green line here is sort of the difference between these two, which sort of indicates that because the minimum is sort of the proof of this is the minimum delay we can have on the path, and then the maximum is added to that. So that is something that could be related. It doesn't in itself say that Bufferbloat exists, but it's sort of a hint that there is some delay that could be taken away. And then we combine this with various ways to try to see if this was actually bloat, if this was related to queuing. And one of the ways we did this was trying to look at individual connections, saying, okay, once we use up the whole bandwidth, delay suddenly starts to skyrocket. So that is one way of saying there's at least some bloat here. We don't know if it's all of it, but there's some there. So we sort of concluded that we have a lot of latency variance in the internet. It has not improved over time, whereas bandwidth has gone up, latency has not. And there's some significant regional differences between continents and countries and so on. And at least some of it can be attributed to queuing, like we saw here. So, as you can see, I'm going through this rather quickly because we need to go through all of it. If you watch the mouse down here, this is an indicator of how far along we are. When you get to the end, we're done. So the next thing we looked at was queue management. We have 3 different papers that look at various ways where, as the timeline we just saw before, what can we do about this Bufferbloat phenomenon? Can we use different queuing algorithms to fix this? And the first study we did was, which is in paper 2, the good, the bad, and the Wi-Fi, where we measure different algorithms against each other to see what is the state of the art today. And then I have a follow-up that with a sort of more theoretical analysis of one of these algorithms, which is also the one that Luca showed on his last slide, FQ-Cobble. And then in paper 4, we build on these different algorithms to have something that's deployable. And that was on that slide. What I just said. So this is the comparison of the different existing queuing algorithms, where P5O, first in, first out queuing, is the current default, or was at the time, where you have a lot of delays. The graph is sort of flipped so that the more up and to the right you are, the better it is. And as you can see here, this is sort of the default. These are the different A-red was one of the things that Luca mentioned, the random early detection in an adaptive version. So these are some of the algorithms, and then you have these Spanish queuing algorithms that also split up the time. I'm not going to go into detail about how these algorithms work, unfortunately. But as you can see, we go from 100 milliseconds of latency to almost 0. And we also go up a bit, which means that we're also actually increasing the throughput while getting less delay on these algorithms. So that was the good part. We actually have algorithms that can help with this. Then we have the bad from this paper, which is we also look at what happens over time when we start up a lot of connections at once. So this is a timeline where at 5 seconds, we start out a lot of big elephants start marching in, and suddenly you see you get a lot of delay, and it takes quite a lot of time for some of these algorithms to get back down to a reasonable level. Except, again, the Spanish queuing algorithms don't care, we just go around. So this was also the analysis of the existing algorithms, and as you see, the brownish squares down here, that's the FQ-Cobble algorithm. So we sort of concluded from this study that the combination of Spanish queuing and prioritization of some of this latency traffic is pretty good. So I thought, okay, let's look into this some more, the FQ-Cobble algorithm. And so I did this analysis of the algorithm. So the reason for this is that it has an optimization where if you have a very small flow, it will get temporary priority. But it's sort of a bit fussy how that works. When exactly will you get priority? It's not sort of, it's an implicit mechanism from the algorithm. So the point of this, and unfortunately, again, I don't have time to go through it in detail, but the point of this is trying to express under which conditions do we actually get this priority. And this is sort of the analysis. It has to do with the length of the packet and the number of the flows and the rate of the link. And then you have this computing theory, the expected actual delay that you then get from the algorithm. So now we're at the point where, okay, we have all these algorithms that can actually solve this problem, but how do we deploy them? So obviously having all these in a lab in theory is all well and good, but we need to have them at the bottleneck where the queuing happens. And there's a number of sort of more engineering practical problems with this, because there may be several billion devices around, like all your routers at home, all these kinds of things, where you can't necessarily fix all of them because they're old. The manufacturer doesn't support it anymore. There's a lot of things that means you can't actually just install the algorithm at the bottom. So what we did was we developed this cake algorithm. I think the acronym is Common Applications Kept Enhanced, but we just called it cake. There was another algorithm you saw maybe that was called pie, so that's yeah. So cake takes SD cobble and it adds traffic shaper, which means you can now shape the traffic so you move the bottleneck to where you can control it and hack it as algorithm. Then it has some other nice to have things in your home gateway. Maybe you want fairness not just between different flows, but also between your different devices at home. Diff-serve is a mechanism to classify traffic in different ways that it handles in a nice way. And then this act filtering is a mechanism to thin out some of the packets that we don't actually, in all cases, to go through. So all this is sort of in a convenient deployable packet. There's a single command you write in, and then this is turned on, and your interface is not really nice for home browsers. So in summary, queue management does help. This fast flow optimization of FQ cobble works really well, but only if it's deployed at the bottleneck, which cake. However, what I didn't show from the graphs I didn't show here is that once you have the Wi-Fi link, things get a little bit more complicated because now you're sending things over the airwaves and so on. So Wi-Fi is sort of a whole section of its own. And we have 3 papers going into that. So we have Bufferbloat problems in Wi-Fi still. We also have this thing called the performance anomaly, which is if you have a station that's really far away, that speaks at a slower rate than all the other stations, you will end up having to speak really slowly to be heard far away, which takes up a lot of time. So you will end up spending more time transmitting to the slow station, which will make the whole network go slower. We fix that. And then we also look into this thing where you can actually enforce policies on the network. This is a diagram of the internals of the Linux kernel. And obviously, as you can see, this one fixes the problems over here. And what this means is we go again from the logarithmic scale, an order of magnitude improvement in latency on a Wi-Fi network once we apply this. It's sort of taking the same principles of a better queuing structure and sort of integrating it into the intricacies of the Linux kernel Wi-Fi stack. Then we also look at the performance anomaly where we have this airtime fairness scheduler where the basic idea is if you have a station that's really far away that you spend a lot of time talking to, you sort of you time how much do I talk to that guy, and then I would speak to the other guys as long. So sort of it's the same basic fairness mechanism. You go round robin between them, and that means you can go from this case where this is the slow station that takes up 90% of the time to this case where everyone takes up the same amount of time speaking on the network. And what this means is that the throughput goes up. So these are the 2 fast stations. They go a lot faster, and the slow station goes a little bit slower because it gets less time, but it's also slower. So the aggregate average bandwidth of all stations in the network goes up, so your whole network works more efficiently. And this was also part of sort of the one. It sort of fell out of the other thing. Once we have the queuing structure, it's pretty straightforward to apply this and get this way. There's some details. Now, once you have this enforcement mechanism to make sure that everyone gets the same amount of airtime, one of the first questions I got when I initially prevented this is, but what if I don't want that? What if I don't want everyone to have the same amount of airtime? What if I want to say, my TV, I want to give that a higher priority so that I can actually watch my movies, but I can't move it closer to get it a better rate. Or all sorts of different, I want a guest network that no matter how many guests I have, they should only have half the capacity together, all the different things. And so building on this work, we started implementing a policy mechanism where we take the same enforcement mechanism and then we build a policy module on top saying these stations should have more bandwidth than the others, you can group them and these kind of things. And this looks like this. So these are two different tests of the same stations where on the bottom one here is the normal fairness thing where they start with an interval. So this guy starts out with almost the whole, and then they share equally as another one's added. Whereas at the top here we have set a policy that says that the pink guys should have half of the capacity, and then the others can share the rest. And as you can see, that is also exactly what happens when one starts. It's half, but then the pink keeps half of the capacity, even as we add stations. So in summary, the Wi-Fi improvements, we have a queuing structure added to the Linux Wi-Fi stack, which fixes Bufferbloat in Wi-Fi. We have an airtime fairness scheduler that solves the performance anomaly, and we have a policy enforcement mechanism for Wi-Fi. And then the reason this is de-emphasized a bit is that we also looked into an interaction between another Bufferbloat mechanism that was added in the Linux kernel at around this time as well, but I didn't have time to put it in my slides. But again, each of these gives sort of an order of magnitude improvement in capacity. So that was Wi-Fi. Then moving on to ludicrous speed networking. That is the paper 8, which when we started looking into different networking performance issues in Linux, there was a parallel effort, which is we want to go really fast, like Wi-Fi and Bufferbloat and so on, sort of the small routers you have at home, but in big data centers, you also want to be able to process packets at a ridiculous rate, which like at 10 gigabits per second, it's up to 15 million, almost 15 million packets per second, and at 100 gigabits, it's 150 million. So you have sort of tens of nanoseconds to process each packet. This turns out to be pretty difficult to do in software. And the normal Linux networking stack is too slow for this because it's built to be very flexible. It can do a lot of things, but that means it's a bit slow. So this is pretty trendy. There's a lot of things happening in this. There's like kernel bypass solutions, the DPDK framework. Cisco has this vectorized packet processing that's built on top of that. And that's one reason to do it. Instead of having this big, slow operating system, we just bypass it and put the packets directly into the program. But that makes it hard to integrate if you actually want to use the rest of the features in the Linux kernel. There's also some solutions where you can do sort of half bypasses and so on. So what we looked at here is this thing that has been built into the Linux kernel, which is sort of this is the Linux approach to high-speed packet processing. It's called the Express Data Path, XDP, because as everyone knows, X is the fastest letter in the alphabet. And this is the architecture of this in Linux. So you sort of the main thing is you add this hook where the packets come in from the hardware. You can immediately start processing without allocating memory and before the networking stack starts looking at them. You can run your own program here in a sort of a virtual machine that builds. It has a lot of benefits. It's integrated in the kernel. It selectively uses kernel stack features. It has a stable API because it's part of the kernel itself. You don't have to read, like if you find out that, okay, this packet actually needs to go up into the operating system, you just do that immediately instead of having to send it back. And you can sort of add custom processing on your application server before the normal processing. And it also sort of scales with the CPU time. So we did a performance analysis of this. So the green one here is DPDK, and the orangey one is XPP. And you can see we get to, on a single CPU core, we go up to 25-ish million packets per second. And DPDK, it doesn't quite have the same performance, but bear in mind this difference is on the order of, I think it's 18 nanoseconds per packet. So it's at this speed, it's actually a very small overhead. But we also believe that the other benefits of XPP sort of makes up for this performance difference. So XPP is sort of the integrated feature in Linux. It combines speed and flexibility, and it's supported by the kernel community. And this has been developed for several years, and of course, I didn't do all that. So I did this work together with the core developers in the Linux kernel, and sort of wrote up the paper that describes it. It's been gradually integrated into the Linux kernel, but so far has lacked sort of an overall description of the architecture that makes it in a coherent way. So that was what we did. Wrote this paper, and we did the performance benchmark. So I'm going to end with this, my thesis in one slide, which is sort of the summary of everything we've done. There's the measurements of Bufferbloat in the internet. We have the evaluation of existing Bufferbloat solutions that I showed before. We have an analysis of the sparse flow behavior of HTTP. The cake integrated queuing system for home gateways, which makes it possible to deploy all this stuff. Then we have a solution for Bufferbloat and for the performance anomaly in Wi-Fi, which is also integrated into the kernel. Building on that, the solution for enforcing policies, airtime policies in a Wi-Fi system, fix for the TCP small queues, interaction with the Wi-Fi system. Then we have a description and evaluation of HTTP. And then the last one is the Flint tool, which I haven't added into the slides because I thought I didn't have time. But since it seems I do, I can talk a little bit about it anyway. So Flint was, a lot of this, as you saw, is experimental work. So I got tired of running experiments manually and started writing a tool to help me automate tooling. And this sort of grew a little bit and turned into a tool that is now widely used in the Bufferbloat community, and I've described this in a paper. So these, as you may have noticed, these 9 points sort of correspond to the 9 papers. And as I said before, most of this, with the exception of number 6, has already been published, and most of it is included in the Linux kernel, or in the case of Flint, it's published as a separate open source tool. So, thank you.
Thank you very much. As announced before we continue with the position, we have a break of 5 minutes.
Computer science.
Sorry, you have.
Oh, I will go that way.
Sorry, you have to take it that.
I'm usually curious, but I have a current method.
Oh, the rock, you see the rock is blocked. So.
We go that way.
Fick lite återkoppling kring ljudet. Det tog upp mycket hostningar och sånt där. Så att vi framöver så får vi se om vi kan få till någon mycket.
Ja, det går inte. Ja, men det är inget man kan göra.
Nej, men det är bara...
Så. Men du, Stefan. Det blir ju lite, alltså då borde man ju nästan ha alltså sådana myggor.
Ja, men det sa jag inte det. Hur mycket?
Ja, kanske så.
Jag tror att det kan finnas något.
Nej, det fanns inte det här. Så.
Okay. Men den behöver ju gå in dit.
Ja.
Inte till ljudsystemet där.
Nej, och det är problemet. För den där myggen den brukar ju gå till den här proprietärt jävla mixerbord.
Men det kanske finns en Bluetooth-sändare bara. Eller något sånt. Eller att du har typ en Bluetooth-headset. Det behöver vara ganska lightweight så att man inte ser ut som en robot. Det finns ju en del snygga.
Ja.
Eller om det finns något som man bara pluggar i.
Ja, för grejen är att du måste ju ha mer än in också.
Om du ska, det beror på om du har presentation. Men har en sån där situation, då funkar det liksom att sätta den där brädan. Alltså den där micken tar upp ljudet härifrån. Det är väl det som är lite, när den är placerad sådär.
Ja, för att jag ville att han skulle ta upp ljudet så mycket runt omkring. För annars när han flyttar sig så försvinner han ju.
Men frågan är, när den sitter så, tar den inte upp det här ljudet mer än om man hade...
Nej, jag vet inte. Mikrofonen är ju upp. Mikrofonhålet är rakt upp. Ja, det ser ut som mikrofonhålet är rakt upp. Så att
det tar ju upp riktigt bra ljud i 415 och sådär.
Ja. Så vi får se. Ja, men det är svårt det där. För samtidigt så... Ja, eller så får man ju ta in ljudtekniken helt enkelt. För ett mixerbord så är det nog att hantera det här sen.
Som alternativ att han stod där. Jag kollade lite grann på YouTube-streamen. Precis när du påpekade så var jag på väg att skypa dig och säga att typ penna kameran så att den kommer med. Så att antingen så spelar man ju alltså honom när det går fram och tillbaka eller så. Men då måste man ju sitta med den där då och styra den.
Ja, det där är lite klurigt för han är inte så smooth. Så du såg kanske på YouTube-streamen. Han hackar en del när den flyttar kameran så jag vill inte göra det för mycket för det blir inte så snyggt. Och dessutom så är han reversed. För han är ju tänkt, alltså när jag trycker vänster här.
Jag tänkte att du tittar på den.
Så jag, vilket även strömmen här är. Så att det, om du tittar på den här strömmen här så är det inte när du kollar på det. Men när jag är här så är det reversed.
Det var ljust och fint det blev.
Det blir det nu.
Ja, men jämfört med hur det var förut.
Ja, men det är när jag zoomar in på, alltså det är kameran. Jag kan inte, när jag zoomar in på skärmen så är den så ljus så att då blir allt annat mörkt.
Ja, det kanske var därför som det så mörker ut förut.
Däremot så...
Fick du en rätt ljudkälla då? Eller?
Vad sa du?
Fick du en rätt ljudkälla?
Ja, jag fick det. Ja, han var rätt. Det var nog jag som bara trodde att han inte var rätt. Jag har ingen aning om jag skulle göra det så tog jag, men det är en liten knapp här. Okej. Där står det ju. Ja. Vi är ju live nu. Nej, men visst, vi får väl få in mer professionellt folk.
Kompetensutveckla video.
Vad sa du?
Kompetensutveckla. Eller nej?
Du tror det är för långt framåt så hamnar du i bild.
Okej.
Så.
We start now with the second part. With your permission.
Okay. So this part is going to take more or less 5 hours. Be ready. All right. Let's start with the general introduction. So Q&A on the introduction. So you started talking about sources of delay in the internet. Can you say more about the different sources of delay in the internet? Well, let's start with this.
Yes, so there's various different things when sort of the signal goes from one end to the other. One is sort of the speed of light propagation delay from one point to another. That's like one we can't really do much about. Then there's routing delay, where the packets go a roundabout way. Serialization delay, where when we have queuing delay, obviously. Application delay, where so processing delay at each point at the endpoints. So you sort of like the main thing. I think that's okay.
So the first question is about. So you mentioned speed of light first.
Yeah.
Then you have routing. So speed of, you pay multiple times speed of light. Then you pay also what you mentioned, which is transmission delay.
Yes.
Which is maybe serialization.
Yeah.
Yeah. And so at first, and all these delays used to be optimized in several ways. Like for instance, routing. You try to get a shortest path, right?
Yes.
To get the minimum number of transmissions across different wires as possible.
Yeah.
But if you pay, if the path is long, it's going to be long.
Yeah.
Nothing. And the why queuing delay is so important, and why is this core of your PhDs?
Yeah. So one is because it's easier to do something about than the speed of light. But also because it tends to dwarf all the others when it's really bad. Like Bufferbloat can be on the order of several seconds on a link which has a round trip time of 3 minutes. So it was sort of for me, it started out as a way to fix my own internet connection at home, which was really bad, and sort of got into this Bufferbloat thing and got interested in queuing. And discovered these orders of magnitude improvements that were possible just by fixing it.
All right. So I guess your use case is also the one that motivated the Bufferbloat effort project from the very beginning when you guys had a problem at home.
Yes, that was like
so you're right. I agree with you in the sense that everyone has been optimizing all the different components of latency, and then we have seconds in some cases in the network, nobody fixing it. So, which makes the point about we need to fix it because we're talking about order of magnitude, sometimes seconds. Let's talk about the impact about delay on applications. Like, what is the relationship? You don't talk much about this, like in the manuscript, but there's an important relationship between delay, like you described in your thesis, and the delay as is perceived by the application, because the application can be very different. Video, real-time video, voice, a mix of them, like the application for a mixture of different flows with different constraints and stuff like that. So this can be difficult for an application developer to deal with all these different constraints. But how do you see the link between the network and the applications, and how delay is perceived by application developers?
Yeah.
How do you manage that?
So like the main point is that once you add delay, you can't remove it again. Like it's all additive, so an application has to pay the cost of all of these, like both the processing cost itself and the network. So the network is a necessary but not sufficient condition for having low latency. There's lots of things that also need to be taken into account of the whole stack, but you need to have like a network that can offer low latency before you can do anything else.
And what are the tools for the application developers to multiplex all the different delay needs into the network, like APIs, transport protocols? What is the flexibility that you have to communicate with the network? Which kind of latency budgets and needs they have?
Yes, that is one of the difficulties. That there has been different attempts to do like this. So if you can set markings, but there's nothing that sort of works end to end reliably because everyone does their own thing, and when you traverse different networks, you sort of get different points. So like one of the nice things about FQCoddle is that it's all implicit. If you send a little bit of traffic, it sort of automatically gets priority through the network. So you don't need to do anything in additional as an application.
That's fair. The internet is not only TCP, right? The internet is also RTP, other protocols. Even if the internet is an IPv4 internet, maybe you just TCP in many deployments, but there are many protocols trying to optimize different objectives.
Yes.
And this is also how application developers try to communicate to the network.
Sure.
These are my needs.
So like the problem with TCP is that you have head-of-line blocking, right? Like if you send something, the TCP stack will take over and it will retransmit for you, and that adds delay, and you can't necessarily do anything about that. Whereas if you do UDP instead, you can send, like you can do your own multiplexing. If the application knows about which messages are more important, you can sort of prioritize those and send them either on a separate flow, or you can, if there's the quick protocol has this, HTTP has a notion of, HTTP2 has a notion of different subflows within that you can try to multiplex traffic.
The reason why I mentioned applications is essentially because we're going to go back into the core of the thesis. But I wanted to talk a little bit about the applications, because each application may have a different objective.
Yes.
For instance, what a typical objective is for web application, for instance, is completion time. Like how much time do I need to transfer this piece of data from one place to another, and using, for instance, TCP. Other applications don't have the same objective, like real-time video, WebRTC media, voice, a mixture of them. Like you can have audio, video, synchronized, not synchronized. You can have data with the media, with different delay constants. So let's take completion time for a second. Well, more than a second. But if you have a network that is supposed to optimize completion time using TCP, and when is this important, and how do you optimize completion time? What is the, from more theoretical perspective, the best way you can do, even if it's not possible to implement, to get something that is open, like the maximum you can do.
So like the optimum would probably be to have some kind of end-to-end path oracle that can tell you ahead of time what is the actual capacity between the two endpoints, so that you can send out packets at exactly this rate and have them flow sort of smoothly through the network without queuing anyway. And like there's some of the other developments that try to do like packet pacing and so on, where we try to infer this. But like, the problem with TCP is it doesn't know the capacity, right? So it has to ramp up at some point, and then it's going to hit a queue, and that's going to end at delay. So like one of the interesting points, I think it was also Jim Geddes has also been harping on this. Like for example, for web traffic completion, or like web pages at a certain point, adding more bandwidth doesn't help because of this ramp up. TCP. So that actually is the latency that also is important here. But that is more sort of a consequence of the
So you are mentioning reservation essentially. So which is what approach like an oracle that sees everything, all the resources, and I reserve allocate resources anytime I request.
Yeah.
Okay, so lost network approach, but of course it doesn't work. I was also thinking about more still in a bufferless system, or in buffer multiplexing systems like the internet, where you have essentially multiple sources which are distributed. They don't know each other. They don't coordinate when they use the network and the network multiplexing naturally. Okay. But if you go back to molecular model, I was thinking about, for instance, in job scheduling theory, we know that there are ways to essentially reduce the completion time of all jobs. So
right, you're talking about shortest completion time. First, shortest.
That's right, shortest remaining processing time.
Yes.
So shortest remaining processing time is a well-known job scheduling algorithm that allows. Well, it's proved that even under stochastic workload, which is where we'll be talking about here, is the best candidate. But that's a problem because it sees the future. So you assume that you see the remaining time flow. So you must know how much time is flow, when it's going to complete, essentially.
Yeah.
And this is where mice and elephants come to play.
Yes.
Can you say something about the nature of the traffic, the characteristics, and why mice and elephants?
Okay, I think I know what you're doing. Yeah. So one of the interesting, like a lot of the queuing theory models assume Poisson arrivals, right? Which does not fit on the internet because internet traffic turns out to be self-similar. So it's very heavily tailed. So you have a few very big flows there's not very many of them. There's far between them, but they take out a lot of the total bandwidth. You have one flow of 10 gigabytes transfer, and a lot of really small flows. That flow is going to take up a lot of stuff. And this the self-similarity for the shortest remaining completion time means that theoretically the amount of processing that has already been done is a good predictor of how much still remains to be done. So that actually helps with shortest remaining processing time because you have a lot of very small jobs and they're not going to impact the big transfer. Like a lot of mice is not going to impact one big elephant so much. So that actually helps. Like shortest remaining processing time becomes a really good way to share the traffic.
Yeah, I was adding into that. So there's been a lot of work in trying to approximate shortest remaining processing time, and sometimes tracking or predicting the remaining time, but it's very hard. Stateful, etc., etc. Now, there's a relationship with what you've done and the optimal objective I'm talking about, which is fairness. So fairness has some relationship with shortest remaining processing time, as in some cases, especially under mice and elephant workload, it's very close probabilistically. So you get something that is reasonably good with respect to it. So this was just just a reposition also.
Yeah, like the sort of the sparse flow optimization that can cover sort of goes in that direction, right? Because you have a small flow that gets priority and it doesn't hurt the big flow so much, and it happens without marking.
I'm not sure. Let's go into that. Like when we talk about spark flows, the first thing for later, but so the spark flows. Yeah, and what is the relationship to alpha and mice? So there are two things. So usually mice and elephants are related to the size of the dog. So that's like a fine size, right? So or the duration of the flow, if it's not fine, it can last for very long. Mice is going to be very short. Like you can have you can have voice application that can last for hours. Then okay, my mother, for instance, or the same classification at 2 seconds. So it's the same application, and can be partial for people. And one is an elephant, and the other one, I'm not saying my mother is an elephant, but one is the elephant, and the other one is the that is not related really on the side of the job, but it's more related to the characteristics of the flow itself. Yes. Like the way the flow is sending traffic into the network, right? And so this is related to spacing. You go back to spacing data. But still, there is a relationship. It's not immediate. Like when you so we're going to take all the questions once, but we'll go back to that. So let's keep this in mind. So these are two distinct things that you can have an elephant, which might be like all the time with your three-photo mechanism. You can have an elephant, which would be a structure.
Yeah, but like for voice flow, you're not necessarily optimizing for shortest completion time.
That's right.
Depending on
That's right. Now, then we'll just make a point about the difference between which kind of characteristic is included in the sparse flow and which one is not. But there is a long-term, actually, not immediately evident relationship between the two, which is related to factors. We go back, which is much more famous. And there you get the link to the elephants and sparse flow. But we'll go to that later. Let's continue the intro for a second. Just a few questions about the community system schedulers we've been working with. There's a nice picture, I think slide number 16, where you show yes, this one, where you show several algorithms, schedulers. I guess they're all available as implementations in the Linux kernel.
Yeah.
And so this is your baseline. So essentially, you took all the available implementation in the same kernel, and then you run all the experiments in compare. Yeah. Now, if you look at this picture, it looks like well, you chose to show this picture, but there are many others in the manuscript.
Yeah.
I take this picture, I would choose a FQ code, right? Like the best one, right? Yeah. If I look at all the other pictures in the manuscript, in the paper, there are many which are almost equivalent. Like in the FQ, it can also be SFQ. And in the performance figures, you show there's very little difference between them, with some exceptions. With the exception of some workloads, right, or load configurations. Why?
So part of it is a matter of scale. When you have to have a FIFO queue in the same graph, it's really hard to distinguish the technology because they all give such big improvement. Like if you, there is actually a factor of 2 at least between SFQ and FQ columns. It's just because there's a factor of 100 up to FIFO. So, but I think a lot of the problem with Bufferbloat isn't like it's not. We don't necessarily have to find the optimal algorithm. If you look at the internet as a whole, we just need to do something because what we have now is like 1,000 packet FIFO queues.
That's okay, but let's focus on let's zoom around SFQ and FQ.
Yeah.
Let's assume we have a family of algorithms that are reaching some optimal point.
Yeah.
Which is probably very close to which is an approximation of what we were saying about shortest remaining processing time. So there is an optimum under this stochastic workload, and then we're getting closer and closer to this point, when you don't talk too much about SFQ in your paper, or at least how SFQ is made. What is the main difference between SFQ and FQ call? The core mechanism. So they are composed of essentially two mechanisms. To a core.
Two things. So they also like FQ call was based on SFQ in terms of the code and so on. And obviously came before, but like there's two things that FQ call does differently. One is the cuddle part of FQ, where like
so it's the AQM piece.
Yeah.
So there's no AQM in SFQ.
No. There could be. Like there is an SFQ cuddle in implementation, just not in Linux. But that's like one thing which sort of helps with like we also just I don't think we say so much. I say so much about it in the paper, but we sort of also distinguish between interflow latency and intraflow latency. Like the latency, so the latency measurement flows that we use as a separate flow from the TCP flow that measures the bandwidth, which is one measure. It's like that's the the mouse is a different part, but there's also applications where you also want to lower the interflow latency, so you can send a lot of data but still get feedback.
That's fine, but let's go back to the differences of the mechanism. So we're saying AQM.
Yes. The other thing is the sparse flow optimization, which SFQ does not.
All right. So how much of the difference between the two is due to the absence of the sparse flow optimization to SFQ?
All of it.
All of it. Yeah. All of it?
Pretty much.
Yeah, but then, well,
I think.
let's say you see almost.
Okay. Most of it.
Must be almost. It can be because otherwise I would say, okay, but if it's all of it, then why would I implement an AQM?
No, like for this graph, because like for the interflow, like if you have a separate measurement flow in SFQ, it gets sort of into the round robin scheduler, and that gives you sort of the average bandwidth. Whereas with FQ cuddle, the separate measurement flow always gets priority on the set. So in this graph, that's like the difference between the green dot and the yellow dot is the sparse flow.
The sparse flow. So, and my question would be, what's the cost of using FQ code? I mean, I know SFQ code is very complex, very fast, very efficient. What if I added sparse flow optimization to SFQ and let's say no AQM and stuff? Would you be happy? Or what about AQM?
So yeah, that is, I think the sparse flow optimization is a win across the board.
I agree with you. I buy it.
Yeah, and like in terms of implementation, it's like it's Eric Dumasay that wrote the code. Like it's really efficient. It's like two checks and a go to implement the sparse flow. It doesn't add anything measurable to the SFQ code. So, but actually the reason there's two variants of FQ cuddle here is like the FQ no cuddle is basically FQ cuddle with the AQM. Because I wanted to test, and like in this test, it gives like
I want to hammer a little more on this point because anyway, so SFQ is very close to the mechanic work I mentioned, right?
Yeah.
Early 90s, 90.
Yeah.
Then I think the Lachman, the labs, he published another work, 98, where he added to SFQ longest speed drop.
Yes.
So SFQ in there is actually any one with addition for definition plus longest speed drop. Longest speed drop. Longest speed drop is very important in SFQ.
Yes.
If you it just you take the original 90 algorithm without longitude drop, just won't work. You would have just basically another different 90 paper thing or 90 not before that remember, but so they show longitude drop is necessary. Now, and this is my maybe we don't stop, but if you look at how longitude drop works, okay, very simple. You drop from longitude. and you look at how FQ is working in the long term. So when you have traffic, right?
Yeah.
And you have these cordial queues.
Yeah.
What is it? When you compare the behavior, if you just look at the time when the packets are dropped, just the point process where packets drop, they arrive, they drop, you compare the two, comparison analysis just like a black box. What would you see?
I would expect them to be smoother for FQ cuddle. The cuddle part smooths out the graph. Like it is, we start dropping packets before we run out of queue space. So that we can, like, it's sort of supposed to tune itself to the TCP loop pattern, right? Which is like, that's the difference between cuddle and microfast. You actually, because you react quicker, TCP gets get a better signal and it can tune itself better to the bandwidth. And now that you went through all this, I just remembered another difference between SFQ and FQ cuddle is also it does longish queue drop, but it drops from the head of the queue instead of the tail, which also turns out to help a little bit. Like it's from a sort of steady state point. So
That's right.
Yeah.
That's right. But at the end of the day, if you look at so you're right, like it's smoother because an AQM is supposed to help TCP instead of hammering TCP. The longest queue drop, it started like a FIFO drop tail to the longest flow, to the longest queue, the queue of longest queue for that flow, and so they can be bad for TCP, right?
Yes.
But definitely, if you look at the point process, you would see more or less the point process very similar, because if you have a given TCP flow, which is sending a lot of traffic at a given time, it's going to be sending traffic at the same time for the two stages, more or less.
Yeah.
And so they're going to fill the buffer at the same time.
The output from the queues.
And then you're going to see the two queues of this guy. So at a given time, he's sending a lot more. Maybe later, no, but now, yes. And then you see these two queues growing, and then you change the loss process. That is, in the two cases, the guy is going to be hammered.
Yeah.
Right. Now, so they're similar. One is better for TCP, also because the other one can also use ECM, right?
Yeah.
Well, the other one typically is not going to do that, which is good because it may reduce losses. We didn't talk about that.
No.
FQ
cuddle does ECM by default. But I think I turned it off for this particular test.
And so my question is now a more complexity analysis of the two, because we were saying very close. And by the way, the spiral flow optimization is something that's been also it's one of the modifications that SFQ made also Jim Roberts was called the priority for queuing, which was SFQ plus.
Yes, I think priority for queuing has a single. But I think that's most of an implementation.
Yes, implementation.
In fact, it's very similar.
Yeah.
Yeah.
And so my question is, what is can you compare from a complexity point of view the two approaches, SFQ and FQ product, in thinking about that is worth the pain or the implementation, or in the end it's even better, or you compare? How do you, if you have another graph like about the cost, implementation cost, but also CPU cost, what is the cost of using these algorithms? The Python is very cheap, right?
Yes.
So it's very bad. What's the cost of all these?
So this is one. This depends on how you're implementing it. So in Linux, it's almost the same. Like there's no measurable difference in terms of execution cost for CPUs between SFQ or FQ code, because you can do pointers and you can just move the queues around and everything. But one of the when we were discussing this, like going through the IETF process, for example, you have big iron vendors who want to implement this in hardware. And now you suddenly get a lot of I have a bit of a fuzzy idea about how hardware routers work, but apparently you need physical transistors to implement the different queues.
Okay, let's take this approach to classify them. What would you implement if you were the guy who's going to code this in a PGA or in a real system? What would you choose?
Well, I would see if I couldn't manage to do FQ codel because the benefit is so compelling, but it is more difficult to do because you need to restructure it. I think it's like no one has done it, but I think it's possible.
I mean, without religion, just say, I mean, you really have, a given amount of time. At the end of this time, you implement it. If you don't implement it, you don't get the money. You do it, you get the money.
Yeah,
you choose. You don't care about the money.
Yeah,
you don't care about the money.
No, but like we have existence proofs for this and all the big, like that is why we don't have a Kubernetes.
So
It is more
what would you do in hardware? What would you choose? Without, of course, trading off performance. Like, if you think, well, height is already there. I'll get all that latency, all those problems, also TCP. But it's simple to implement. But what would you do to get in hardware? For instance, Pi, you can find in some toxicity of one CMTS, right?
I think Pi is sort of my interpretation of what is Pi is sort of a way to get the benefits of Coddle, but you can retrofit it into existing hardware that runs web. So it's sort of a control mechanism for the drop logic of web. So I sort of got that feeling from it came out of Cisco, so you probably know it better than me, but it's sort of
not really. I wasn't there, but no. The point is, including I want to be close to the optimum.
Yeah.
What would you implement? Because those are
pretty far. Well, I would like to implement a queue, but I think it's possible to do it, but I haven't seen anyone try. I think it should be possible to get like a
there's a class of you don't talk about this in the manuscript, but there's a whole class of other algorithms which are still I would say in the class of forward networking mechanism, but not control queuing mechanism.
Yeah, right. The virtual flow chain.
No, I'm thinking about something like approximate thread dropping.
Yeah.
Other things where you essentially have no per flow queue.
Yeah, you have per flow state.
You have per flow state.
Yeah.
Can you
elaborate
more about?
I looked at some of these things, and they are like if you read the papers that describe some of these sort of virtual drop algorithms, they are like the motivation for them is these are simpler to implement. And like coming from a software background, I'm like, what? This is like all this mechanism, all this it's way more difficult to implement. But this is a hardware thing, right? If you don't have the resources to have manual queues, you can have like a state variable per flow instead, or like a handful of state variables, and then you just use the existing drop mechanisms to drop more from flows, but they're still in the same queue, basically.
That's right.
And
and approximate thread dropping is available in Cisco Nexus switch.
Oh, really?
Does
anyone turn it on? Does anyone turn it on?
Oh yeah, I mean, you don't need to configure.
Oh, so why do we have Bufferbloat everywhere?
No, wait a second. It doesn't fix Bufferbloat. It gives you something, but it doesn't give you everything. Like, this is the second question. But the point is, so you're getting hardware. So you get the speed, you get deployment and switches and products because it's very simple to implement. But that class of mechanism doesn't give you zero latency.
Right. No, because you still have to you can't prioritize.
No. Well, you would need an additional queue. You need to do something more. But so the point of the discussion would be essentially. So there's no one algorithm. Essentially, there's a set of mechanisms here. If you're putting this nice slide, but there are other figures where you would put these algorithms, and they are not necessarily just FQ or SFQ, but it is a mixture of mechanisms they are using and exploiting. Like we said AQN, we said flow queuing, we said sparse optimization. In queue drop, all these things are essentially we talked about pair dropping as a mechanism, which is an approximation. And how do you see them in building a system? Like how would you classify them? All the things that are coming out of discussion. How would you? Because they're not. I mean, some of them are well known, others are less known. How do you put them together depending on the different network segments, like access home, medical, core, data centers, residential networks and stuff? So all of them? All of them.
So
I guess you are familiar with the different architecture of different networks. It's you may have ARM, you may have NPUs, you may have silicon, you may have different kind of architecture. And if you go back to optimizing the internet, so in your introduction, you say, okay, I go to the bottleneck, it's the home. Okay, this is the architecture of fix it. Let's take a global view of the internet. There are different places where these things can happen because the home is not the only congested link. So you can have other places, peer links, and so where do you see how do you compose them to get to the end-to-end view?
So like any way you can run things in software, I would do something like electrical. I think it's pretty close to the optimum of when you have the flexibility of software. And like as we saw in the last paper, that's becoming more and more places as if assuming that computation speed goes up faster than bandwidth, which in many cases closer to the edge continues to be the case. So you can do these kinds of things, and then the core is rarely congested to the same point. Hopefully, like when you do traffic engineering in the core of the internet, you try to avoid congestion rather than with queuing with the traditional rule of thumb.
That's right, but in some cases you cannot do that. Like usually, now traffic engineering is a good point. We can talk about traffic engineering later, but you have for many reasons. So the internet is a network of networks. So you have your network, then you peer to another network, you interconnect this guy, and for many reasons you may have a peer link to your neighbor that may be congested. Right? For many reasons, sometimes you want to be congested.
Yes.
You want to be congested for many reasons, like I don't like you, you go there. Or our business agreement goes wrong, you go there.
Yeah.
And you pay more, and your customer is not going to be happy, especially from Google, and you are Lambda ISP, right? So that happens. But you may have a cloning at 90% of utilization. Yeah. So it's not the only place where, but you're not going to put a few code in a peer link using.
But if we're talking about the general internet, I would probably say having just an AQM on these kinds of links would help a lot. Like the main, as I think I mentioned it before, so the main problem is right now we're doing nothing in many places.
No, but I agree. I mean, I think we'll talk about the reconciling this work later. Now I have to hammer a little bit, but the thing is, we've done this. What's the cost to do that? The more the thing that where you cannot go because it's about hardware, it's about cost, it's about deployment, where you cannot software. But I consider also that now we are moving to I have 1 gig per second in my house, right? So I don't know if you can do this in software, sure. At which cost? You're not going to XDP or VPP in my 50 euros box, right?
Why not?
Because
you're mentioning
yeah.
But sure, like there's a point where this is not possible, obviously. I'm not sure it's at 1 gigabit, but so what your question is, what should we do instead when we can't?
If you were the engineer that's supposed to start saying that you deploy this in here, this in there, you can do this in hardware, you can do this in software, and it's going to be cheap.
Yeah.
so you can make a business out of it. How would you use this knowledge to say, now I'm going to put this in here and then put this in there? Your experience.
Am I constrained to algorithms that exist already?
No.
So one of the things, like, if you look at things like FQCoddle, FQCoddle as it is really difficult to do in hardware because it has like 1,000 different queues. But we did some experiment that's especially at low rates. We get a lot of the benefit with something like 16 queues. And sure, that's still going to add stuff to your hardware, but it's not as expensive. So I think there would probably be an optimum point from here where you can get a lot of the benefits by having sort of a FQCoddle-ish kind of thing, like some kind of multiple queues with HOM on top that would get a lot of the benefit of FQCoddle without doing 1,000 queues. And I think that would
recorded the answer is always FQCoddle.
No, like not necessarily FQCoddle, but I really like Spanish game, and having an HOM on top is
No, that's fine.
yeah. But if you can't do that, do HOM.
All right. Okay, let's start with the questions. Okay, this is a serious question about the methodology you use for. So let's go back to the traffic characteristics, measurements, the analysis you've made in Figure 1, the first paper you presented. So can you tell us a little more about the methodology you used to infer some of the things you claim in the paper, like thesis accumulated. Okay. Yeah, because we get all this data, the data set essentially.
I think we actually have this thing.
Yes. Yeah, this thing.
So the measurement study was sort of comprised of two different data sets. One was the NDT measurement lab, big data, like 300 million flows from Google. And the other was a actual packet capture from operation. And we sort of tried to squint at it and see if we can infer that there's probably something going on here. And for the NDT dataset, we did this, which like we get what the data was a trace of latency over time with like all the TCP state machine, Web10G, and data points. And so what we came up with was this thing where if you immediately after the cross is the drop, and then you immediately get a like the next time once the data resumes, you get a significant drop in RTT. We assume that is because you get a drop, so you have your bandwidth and that clears up the queue, and when you start up again, you have a much lower RTT. What's sort of the logic behind that? And it's also constrained about what we could do, both with the data we had and also something that we actually write an algorithm that would identify in the whole data set. And we tried to do this sort of conservatively so that we would rather have too few matches than try to match them and have something different. And so we sort of set the threshold from this. I don't remember the actual.
So these are the samples you get from the state machine, right? You measure it from the time, right?
SRTT. Yeah.
Because the log you have doesn't include all the pickup, right?
It did, but we didn't have the resources to process it.
Okay. Do you think by processing all the pickups, would you have a higher hit ratio in terms of identification?
Maybe. So.
Because you get all the timestamp, right?
Yeah, but you only get that at the sender, and like that's the same.
Well, the vantage point.
Yeah. No, yes, but we don't like so. The NDT data set is everything is collected at the sender.
Okay. Only this.
It's you go into a website and you run a test. So it's random users doing it. It's not a controlled environment. So that's why we combined it with the other data set where we had a vantage point. That was the this thing, right? Where we actually have the measurement.
Yeah, you have the little figures.
Yes, and it's on it's like an aggregation link inside a network.
Did you make the analysis for this sample? The identification, I mean
like the same one?
Yeah.
No.
Okay. But do you think you will be able to increase the hit ratio in terms of identification? In this case, where you can see all the packet, all the timestamps.
Maybe, but what you could do is you could verify that it's working. You have like here you can actually know from this vantage point you can see the bottleneck presumably. So you can verify that the algorithm works. But I'm not sure if you get more hits necessarily.
Okay. Because there's another thing when you identify human latency that you're experiencing. So in some cases, it may also be a question just of available BDP, right? How much bandwidth product is available in the network for this connection?
Yeah.
Because you have this vantage point, you have several sources, they have all different RPPs, they have all different BDPs, and so they're going to behave differently. Because in some cases, a given connection can have the full BDP, in some cases less than that, in our cases a lot more than that. And do you think you could use this knowledge to get more, which means flow rate plus latency measurement? Here you just use, in the first analysis you were just using the TCP state machine RPP as measured by TCP state machine.
Yes.
In this case, you essentially measure the delay by the first diagram. You never use the TCP rate, right?
We do in these things we look at rate with but I don't think we did that for the other data set. Like we look at rates to see whether or not they the aggregate bandwidth has increased. But we used the drops direct. Like we had, I think the reason we didn't look at rate was we had the drop information with the red cross. We know the point in time when a packet dropped.
Okay, that's fine. I had another question about this paper, which is about one thing you write is that the distribution of the latency is everything. Where do you see it?
Sorry?
Where do you see it?
Where?
Where? Because you say you can see it's everything. I didn't see it, for instance. Where is that? If you can see, okay, this is everything.
So these, I think it's because these graphs are cut. So, like this one actually continues up to like about here.
As every other distribution.
Yeah.
So what would make you claim that it's everything? The cake, first of all. But not the existing of the cake, but the form of the cake.
Yeah. No, we didn't match it.
Okay.
Like it was sort of that was maybe a bit hand-wavy.
All right. So you make some correlation analysis, which is the other part.
Yes.
If you you show there's also another one, load, right? No, rate and load. No,
just these.
just rate. Okay, rate is the flow rate, right?
Yeah.
And the flow rate is measured as completion time in bytes, right? This is rate, right? You define rate as
Bytes over time. Yeah.
okay, that's what. So it's the average rate. what other variables would be used to correlate? Because this is useful to you can get something like more, but it's useful at a certain point. Like the fact that I have a very good throughput doesn't mean that I am low to time. The fact that I have what are the variables that are for sure positively correlated with high queuing latency? I can have a super fast load, zero latency, because maybe I have throttle or I don't know, and I go 1 gig per second because my link is able to provide it. Right? And so in that case, queuing delay would be 0, and so it would be negatively correlated or even insensitive, like completely independent to this variable.
Mm-hmm.
So what are the variables where you're sure this variable is positively correlated? What kind of measurement you would seek for
when you do the drops, like if you
drops, for instance? Seems like
if drop rate goes up with delay, then you might be hitting the capacity to do that.
utilization, maybe. Utilization where you need to have a link.
Yes. Oh, right. Okay. Yeah. So like this thing is obviously not the actual link visualization. We're just
Yes.
inferring that this guy has a 5.5 megabit link because it looks suspicious that that's his capacity. But that,
It's a signal, but it's difficult to measure because you
Yeah.
need to have more.
yes. Right.
All right. If we go faster, I have a few questions about. Yeah, we talked about sparse flow modeling, the Wi-Fi, and XDP. I'll try to do quickly.
Yes. I have one question for all of that.
All right. So you do an MD1 analysis of the priority queue. Let's go to priority queue, where you get all the packets that belong to sparse flows. Yeah. And you have a packet queue, and then you make the assumption of what code that's on arrivals, and so you have the cluster packet size, and you make an MD1 analysis, and then you have the finite source model, workload model, right? And which gives you, and so you stop saying, okay, this is an upper bound.
Yeah.
Because of that, because the finite population workload. Yeah. Because you cannot have more than a certain number of sparse flows.
Yeah.
So if M is not M, but M is M of N, where N is the number of sparse flows.
Yeah.
Okay. Are you familiar with the finite population model, which you could solve and gives you a closed formula so that you can move from an upper bound to an exit formula?
No, but please do tell.
Are you familiar with the NSET model?
Nope.
No. In Sweden, you should be aware of the NSET model. Anyway, I think you can get to the exit formula if you use the exit model. Because you're very close, you make the simulations, you have a high bound actually, and you see the difference only at high load.
Yes.
Why? Why the bound work very well at low and normal loads, and it doesn't work well when the load is high. When it approaches to 1, essentially you lose
Yeah.
it wasn't there anymore, essentially. Because 1 goes to 3.
Yeah.
The bound.
Well, because when it's like infinite for unreliable, you sort of have the tail that goes up again. Whereas if you have when it's cut off, you lose the symmetry in the distribution.
Say it again.
Like if you have sort of the bell curve and you cut it, then it's not symmetrical in the same way. Like I don't have a precise formulation of this. It's more sort of my intuition about it. It as you approach the top, you have another. It doesn't peter out in the same way as it would if it was infinite. You don't have the very large values or very small values with really low probability because you run into
Yeah,
all
that's theoretically right.
Yeah.
Okay. I think the let's get this. Okay, let's talk about the so in Wi-Fi things change.
Yeah.
Right. In Wi-Fi change a lot. Let's start with the Wi-Fi basics. So when Wi-Fi was designed before B, it was letter B. What was the core objective of designing the access point control the map like that? Why was the Wi-Fi was developed before B? But what was the core objective of doing DCF like that?
To avoid centralization.
There's a first objective, you simply distributed and stuff. But the long-term goal of the access point control was to give to each station a fair access probability. So essentially, each station can have the same probability P to send a packet to the channel, no matter how many stations you have in a. So they focus on that. And would be that something changed, something that's changed in what is the thing that essentially enters introduces what you call what is being called in free paper the anomaly. What is that? Why did you have this anomaly that you try to fix? What did you fix? In B we have something new. It was not in the first release.
Is that the exponential backup? No.
Essentially, you start getting all these rates, physical rates.
Ah, right. Oh, that was in B. Okay. Yes. Okay.
And then you never stop. So like get all these.
Yeah. Now you have like all the field magnitudes.
And this is where you to stop. So this is where you start. You get this anomaly.
Yeah,
what is the relationship with P, the first probability to access the channel, and the fact that you have a different physical rates, which are often because you have people in different distance to the access point, and so you need to have a different physical rates so you have higher throughput in theory, because then with a mixture of channel coding and modulation schemes, you can get a higher packet transmission success rate. I don't why. What is this? It's magic that is magic. This original scene that you get this P, which is fair to everyone. You get different physical rate, and then now you get this anomaly. Yeah, so you can also define the anomaly.
Yeah, so like the thing is, you have the same probability of sending in B one packet, but because you have different rates, that's going to take a different amount of time. So you send one packet, and maybe you spend 4 milliseconds doing that, and then you go back and you have the same probability again to send another packet. So you sort of get equal transmissions, but you take the analogy I used is like if someone is further away, you have to speak slower to them, you would end up taking longer to say the same amount. It's 100% data, right?
That's correct. And what is the long-term result of this?
Throughput paths. Everyone gets the same throughput.
The same throughput, that's right. But if you say like that, it doesn't sound like a bad thing. Everyone gets the same throughput.
Yeah, but
what is the throughput?
You get the lowest throughput.
You get the lowest throughput. That's bad.
Yeah.
Okay, so and then you fix it by using so we move to okay. Now you get the airtime track. So what are you trying to emulate using airtime track? What is the goal of doing it? Why airtime track is the right thing to do?
Because airtime is the actual resource that you're dividing up. Like on a link where you have a constant rate, then it is the amount of bytes that limits what you can do with the medium. But because the medium is transmission time, what you want is to divide up the transmission time fairly between people. So you get like two interesting properties. One is it turns out it's proportional fairness in byte in throughput. And it also turns out that as a station on a network that has airtime fairness, your performance is now no longer limited. It's only limited by the number of stations that divide it. So no matter how, and not by the performance of those other stations. So 3 stations will always divide at the same time. It just means if you're slower, then you don't get to send as much data, which sort of intuitively also it's the right thing to do if you have like transmission time is what we all have to share, and like it's not my fault if you're bad at sending data because you're slower.
Okay, I'm with the answer. How do you compare this with 811AX?
AX?
The most recent one.
Yeah. What are you thinking about?
You're not familiar with AX?
Not that much.
AX introduces essentially scheduling like LTE.
Oh, okay. They do?
So how do you compare a different map like LTE compared to Wi-Fi when you have higher antennas?
But it does TDMA scheduling.
Because one of the things you get with, you said something important, which is if you are maximum fair, well, I translate in my words. If you are maximum fair in time, you get proportional fairness in throughput, in rates. Now, you get something more if you do schedule like an LTE, which is an additional gain, which is called multi-user diversity.
Mm-hmm.
Because when you are airtime fair, you are airtime fair like that. You don't care. It's much me, like everyone. But you don't consider the status of the channel of a given user when you say, okay, I'm going to give you the transmission slot. In LTE, you have an additional gain, which is, okay, I globally, I'm going to be fair. I'm going to be TDMA-like. But I tend to be biased towards those users who are very close to a peak, radio peak, in terms of transmission rates, because the rates are fluctuating.
Mm-hmm.
So now we are assuming that all the rates are constant, like physical rate, no, it's moving, and everything is stable. But actually, we know the radio signal is fluctuating quite a lot. And actually, your physical rate is not a number, but it's a function, right?
Yeah.
Now, multi-user diversity exploits that concept. Do you think you can use this in Wi-Fi as well? And move from maximum time fairness to something that, extending what you've done.
Yeah. So,
are you familiar with the multi-user diversity? If it's super quick. It's
not the Facebook, no. So, I think one of the when I implemented this fairness, that was in F9K to 11N, and then like the ongoing work is sort of to try to generalize that to different types of hardware. When we move to things like AC and F10K and so on, which has new MIMO, we sort of run into this problem there because it's a round-robin scheduler that works by throttling things really hard. Like you also see in the paper, it has an adverse effect on latency and visualization. But also we need to throttle them really hard. So there's this problem like, what if I want to send to these 2 stations at the same time? Or what if I want to do better scheduling, taking into account like propagation?
And this is actually something that you can do in LTE, for instance.
Yeah.
Now probably available almost everywhere, which is power control. Like when you send a packet to in the same transmission opportunity to multiple stations, different packets at the same time, you are essentially using the channel at best. So you can do that at the cost because you have to remodulate the transmission data on the power, which is unique between you and the different station. So this is why it is better. But also,
no question that it's a better Mac in that sense.
But maybe my guess was, what about pushing information about a signal in Wi-Fi, maybe in AX or something?
There's definitely things you could do smarter. So also like not without all that. The problem is that we don't have access to the firmware, so we can't. There's a lot of information we don't have. So that like implementation wise, we're limited in that sense.
Also, you don't have the feedback channel like in LTE. You have the CPI or the millisecond, so of course.
Yes.
Let's go back the last part of the questions related to high-speed packet processing. There is one thing that is there is a relation between what you have just said about AC and actually the high-speed packet processing that I want you to make. I'm going to bring you there.
A relation between AC and higher speed.
And why? Why AC and high speed? How can you achieve those rates in AC? What is the magic?
Yeah, parking.
This one.
Yes.
And then bulking is very important because there's a trade-off between latency and batching and bulking. So you use fusion opportunities as much as you can, essentially. But it has a cost because, as you said, and you see it in your one of your papers, you work on that, and you cannot have everything once unless you have an adaptation of that. Like you try to understand what is the size of the batch. Because if you batch too much for all application in all cases, you're gonna pay latency. In some cases, you don't need it. So well, there's also mechanically let's stop on that. But let's go to the actual packet processing. So you've been you've talked about XTP. XTP and also you talked about removing bottlenecks in the XTP data path.
Yeah.
What is the key idea of XTP and how many bottlenecks you remove with XTP and what's left?
Right. So there's two main, more than two. So like one thing is to run the packet processing as soon as possible once the packet comes in. So like we haven't allocated any memory, there's no data structure that can build, just get a packet buffer immediately in the driver once you get the data. So that removes all the processing you normally have for network stack. You can the drawback of this, of course, is that your program has to pass this. Like it's also like the really impressive performance numbers you get with XTP and BPK as well. Like we can now throw packets away really, really quickly, right? And that's like as soon as you start, you need to do more performance drops for all of these. So it's sort of an upper bound. That's one thing. And the other thing is docking. So in XTP, can
you do it?
Do what?
Using batching, right?
Yes, there's batching now to a certain extent because you have.
I was not aware about batching.
Because you have the NAPI driver thing. So like when a packet comes in, you get an interrupt from the hardware, and then you process that, and that's really slow. But when the link is idle, that's what happens, right? But then you have this. It's a sort of a general device driver thing in Linux, where when a packet comes in, you get the interrupt, and then the CPU will stay in polling mode for a while and see are there any more packets coming. I think it goes up to 64 packets. So if you have packets coming in immediately, you will get 64 packets at once, and then XTP is implemented inside the NAPI thing. So you get 64 packets. You will run in a loop, running for the XTP program and all of these 64 packets, and then you will go on to the next batch. And this gives you sort of instruction cache. You don't grow the instruction cache for the program.
How do you manage it? So okay, batching is important. Yeah. And then you keep essentially so the data path is essentially you need to PCI, but then you have several memories.
Yes.
Because you have DMA, but you also have cache lines.
Yeah.
And if you then you get to the core, and so this data going to the core, and this is where batching can help.
Yeah.
Because you don't need to cross.
Yeah, but that, like these numbers. So on modern instant processors has this nice DMA to cache thing. So this in these numbers, the packets actually go directly into the processor cache, not into memory.
Why DPK is faster? Because
so a lot of it is just sort of micro optimizations. There's like we commented out 4 function calls and we moved half the difference. Like it's I think I mentioned in the presentation. Even though it's almost twice the number of packets per second, the difference in processing one packet is between 10 or 20 nanoseconds.
and the one function call overhead is 1.3 nanoseconds. And so it's just like the driver has had more optimization than DPK. It's sort of like that's about half.
Okay, this is something that is very important because you have one function, one network function, like you move the packet from the NAND to the DMA, you bypass the first I/O, then you have all the cache line and stuff.
Yeah.
The other thing is how do you, because we have different codes to be executed on different packets.
Yes.
And so they are not processed the same way. How can you continue to batch them to the core if they are essentially different flows or different functions, like they have to go through different processing.
Yeah.
Even a simple like lookups, they're not going the same way, right? So you cannot look up both. You cannot batch them because they are not going to the same place. Like no, they are not the same destination address, for instance. Or and it's something that mentioning that because you mentioned DPT as well.
Yes.
So in DPT there is a software framework to manage that. I'm wondering if XDP has already that.
No, not really. So they can do some things in your XDP. So it really depends on what you want to do with the packet. If you just want to send it out again, that's one thing. But one of the neat features of this has is like you can redirect packets. And one of the things is you can redirect them to different
Even
CPUs.
if you want to just cut through, send a packet from one place to just take the application, right? So yeah, if you look up in the pipeline, they go different places. Then you cannot just fetch because of that.
No.
Right?
No, we don't have anything like BPP or anything like that. And I don't think necessarily we will get that either. Like it's
no, because it's a different framework.
But it's also different use cases. Like XD.
I think it's the same use case. You want to send packet out, right? It's a routing.
Yeah, but like XDP is also sort of if you want to do like write network function, virtual network functions,
so more complex things,
and just do that on that hardware, you might be better off doing DPK. Whereas what XDP is, if you want to accelerate your existing Linux machine.
Okay.
So like I don't think we will actually get for all use cases performance parity between the two, but the goal is more sort of XDP is fast enough that the other benefits of the architecture are so compelling that you would rather do that.
Okay, we get to the last question.
I have one.
I mean, last question of this person is like that. So there's still about performance and trade-off between latency and throughput. So we're talking about the XDP optimization, so bypassing bottlenecks in the data plane, in the data path. What about the hardware optimizations? Like hardware optimizations. Like you have several optimizations in all systems. In Linux, you have many others, like I mentioned TSO, GRO, all this stuff. Crypto optimization, everything is made to offload the network stack from doing things that can be done in parallel by hardware, doing always the same thing, right? This has especially in the case of segmentation floating, this kind of operation, they have an impact on, can have an impact if done natively on latency. And also vectorization, the discussion we had about vectorization is not something that I'm not saying you always have to have 255 vectors to your core so that you get maximum throughput, because maybe your application doesn't like it.
Yeah.
Well, how do you trade off between all the, we go back to the application needs at the very beginning of this discussion, which is at the end of the day, you cannot just pick one solution for all, right? So how do you manage that?
Well, there's not one right answer for that, obviously. Or like, that's sort of the panacea, right? To have the one trade-off. But how do you manage that?
In the case, for instance, of packet scheduling or AQM, in some cases, you get throughput on one side because you're using accelerations, and then you lose latency on the other side because you are fetching so much that you cannot schedules at a finite range.
So like I'm sort of of the opinion that we need to pay a lot more attention to latency. Because throughput is what we've been optimizing for.
I mean, pacing is another example, right?
Yes.
And pacing, also this concept that I cannot mesh. So it doesn't, well, I can mesh, but
But differently.
not at much speed.
Yeah.
Right?
Yeah.
I need to tune it to have
So,
some mechanism.
I can throughput for the user. The user doesn't like the user experience. Throughput is sort of incidental to that. The main thing is response time. But I think that you want to optimize the response time at the user level. And depending on which application it is, that gives different sort of low-level trade-offs at the network level. Like, is it flow completion time for this application, or is it latency for this? And
But it seems like the reason why I mentioned that is it seems like we're during the last 10 years, we've got a lot of hardware optimizations for doing things.
Yeah.
And so we have been able to move up in terms of throughput because the hardware was able to do more throughput, the application was able to exploit more throughput. And then we started losing latency.
yes, and now people have
And they say,
started.
okay, you get some advantage on this side and you lose on the other side. And then you say, how can I go back to that?
Well, it seems to be sort of going in cycles, right? Like, one of the interesting things about Bufferbloat is there's this thing where like, Jim Geddes was the one of the main people who sort of started banging people on the head with this. And the academic community in the beginning was like, what is the new thing? Like, that's not news. We already knew this. But because you have these sort of, you see it with Wi-Fi especially, you take one access point and you take a client and you put them a meter together from each other in sort of an anechoic chamber, and then you measure one flow through, and that's your benchmark, and once you've optimized that, you ship. So it's like a lot of this thing, we have better technologies, we have better ways of looking at this, but because you measure things, that you optimize for what you measure, and that is one of the problems. It's more sort of it's sort of a social engineering thing, right? It's sort of a how do you get people to demand better latency? And we
Business.
Yeah.
Yeah, also social, but anytime you have social, you have to.
yeah, no, but I mean, it's sort of a layer 8 problem.
Okay. Okay, I'm happy with the answers. I think I'm done.
Thank you very much. Okay, then we continue now with the examination. And we have the 3 members of the committee. Yes, we can now ask questions. Would you like to start? Okay,
Maybe we do airtime per queuing here.
Shall I time you?
I think we manage. It's this. Why have buffers been loaded?
Yeah, that's a good question. So there's different sort of explanations for this that you sort of hear. One is, oh, memory is cheap, so let's just add more of it. Another is this aversion to dropping packets. We've already expended all this capacity trying to drop packets and sort of not being aware that occasional packet drop is quite integral to how the internet works. But you need smooth functioning. It's actually an important signal. Another is what we just discussed. They can measure the wrong things. So there's not necessarily one good reason why buffers have become loaded.
But colleagues of Lucas and others who are designing the systems, I mean, they must have. I mean, they are engineers. I mean, they don't just guess. They must have dimension groups for how much buffer to put in on an interface with a certain for a certain link and so forth. So
that is also part of it. That, like, at least in the whole router space, which you're most familiar with, you get the same device and it's dimensioned to the maximum bandwidth that it can be deployed at, and then it's deployed at a fraction of the bandwidth. So you have a buffer that's dimensioned for a gigabit, and then you run it on 10 megabit link, and suddenly your buffer is 100 times too big. That has definitely been part of it in sort of the home router space, like cable modems and stuff.
I was a bit curious in your measurements of the phenomenon itself. I mean, did you check any specifications on the equipment? Just say how big are the buffers? I mean, if they're bloated, right? That there's a specification that says that there are 1,000 packets long, and that for that link would translate into hundreds of milliseconds of delay. Which is probably,
So again, in the home router space, the buffer is whatever the default in Linux is, because these are really cheap devices that people ship 5-year out-of-date software on them when you get them, and they just take a random Linux distribution and put it in there, and that happens to have a 1,000 packet buffer by default. So
why haven't you recommended this change of the default?
We have.
Okay.
And it is like FQCuddle is the default in like the OpenWord firmware in lots of Linux distributions and so on. The problem is getting it. There's a lag, so the technology is there. Give it another decade, maybe. Like that's the.
But the first would be to recommend a smaller default buffer size itself without having the fancy mechanism to manage that buffer.
Yes, but that interferes with your one-flow throughput measurements. And also, like, just the smaller buffer in itself, it helps in some cases, but there's also cases where you need a buffer. Like, in the original Cuddle paper, Van and Kathy sort of distinguished between good buffer and bad buffer, right? Like, when you have a spike, you need to be able to absorb bursts, but then you need to drain the buffer into afterwards. And that's why AQM helps.
How much of the discussions from 20 years ago on self-similar traffic, heavy-tailed distributions of workloads and things like that, and Ikanos and some other people did extremely complicated queuing analysis to handle this type of traffic models, and of course they saw that buffers had to grow by orders of magnitude to accommodate for a reasonable loss level. Do you think that has had an influence? Have you heard anyone referring to this type of traffic or anything to justify the information?
I haven't heard that. Like, I mean, using self-similar traffic as, like, the fact that traffic is self-similar, using that as an argument for bigger buffers. I haven't heard anyone make that argument, but
maybe it was forgotten on the way.
Yeah,
sure. Okay, so I can come back to the
Okay.
Okay, maybe I can continue with the what Göran said about why the buffers are big, and as an introduction, maybe give a partial answer to that, which is possibly with the separation of the communities that are designing the links and the IP community. So there's this legacy that your link should not propagate. Okay? You have enough buffer not to propagate. You have link layer retransmissions not to propagate. So that might be one reason. And this leads me to my first question on that in your thesis you have several ways or different ways of battle with the link layer control. So the shaping, the PS view or control view, and then the specific Wi-Fi mechanism. And the papers they show the benefits quite nicely. But could you comment about the drawbacks or possible shortcomings for each of these techniques, starting from the shaping, then control PS2 and Wi-Fi? So do they solve the problem in a general way, or do they each have some possible?
Oh, definitely, yeah. Like the thing you mentioned, like we must not ever drop a packet, is quite, especially in sort of the telco industry. Dave Tatt was also probably wrote a song like "Every packet is sacred" in Monty Python, and that like the disconnect between no, this is actually a function enough in the network. Like we need to block packet communication. So, but to answer the question, like, take shaping, for example, is that I consider shaping as a workaround to move the buffer. And the main problem with that is you need to know the rate. And the rate is not necessarily stable, and you don't necessarily know the normal rate. So we have a whole sort of wiki page on the Bufferbloat.net website about how do you tune your setting. Like you run a test and then you see if the latency goes off, and then you try a setting, and then you sort of do a binary search to try to find the rate. And we spend a lot of time trying to take account of link layer overheads, if it's the DNS, DSL connection, all these kinds of things. So that's definitely the drawback, the shaping. And TFQ.
Oh, we did go back to the shaping. Okay, that's definitely one of the drawbacks. Anything about it? Possible drawbacks, or it possibly makes it impossible to do shaping.
Yeah, it's quite CPU intensive, like, especially on home riders.
Or maybe something.
And you don't get all the hardware activation and stuff.
Maybe something related to the different delays that was not maybe mentioned in the past. So we have a channel allocation delay, right?
Sorry?
We also have channel allocation delay.
Yes.
Also, right?
Yeah.
So there are also many wireless technologies that use channel allocation mechanisms like satellite TV RCS systems that use volume-based channel allocation, where you need a certain amount of data in your buffer before you allocate.
Yeah.
So in such a case, you won't have those packets, so you won't allocate them.
Yeah, like but you have the same sort of, not as an allocation, but in Wi-Fi you can't aggregate.
It's pretty similar.
Yeah. And so that's one of the reasons we started looking into how do we do better queuing in Wi-Fi, because shaping doesn't work.
Yeah, right. Okay, but let's move on here. Yes.
TFQ has the same kind of thing with the same kind of drawback with Wi-Fi. Obviously, like it's also sort of a shaping thing, but it's not, doesn't have that many drawbacks in itself. But it does nothing for the network. It only works on the host where you actually have a TCP socket. So it's sort of an optimization for the endpoint more than it's an endpoint in network.
And more specifically, what is it?
Yeah, sure.
So if you are running quick, for example,
yes.
UDP, then maybe not work.
Yeah. So,
and how do you think that it would work if, so in the paper, if I recall it correctly, it was evaluated up to 8 flows. How about if you have something more closer to 1,000 flows?
Well, it will make it better, but it's like. Yeah, so TFQ is a very specific optimization for a single TCP socket that like it tries to push buffers up to the application layer that but obviously it doesn't solve, it helps, but it doesn't solve it itself.
Right.
It interacts well with pacing though,
for example. If you have 1,000 flows, each having 1 millisecond of data, then it's 1 second. Right.
Yes.
Okay. And then
we already discussed the drawbacks of fan queuing, I think, from an implementation point of view. The drawbacks of AQM, historically at least, has been like the reason why, I think you mentioned it initially, Luca, that red has been in every Cisco router for decades, right? Because no one turns it on. And the drawback, and I think the reason for that is that if you tune it wrong, it will drop way too many packets and you will completely destroy the bandwidth. And so that is a lot better with the modern AQMs that also tune, but you still have some, they are built also as an optimization to a specific sort of feedback loop, that's the TCP congestion control, right? So there are definitely applications where you will get too much dropping. If you have BBR congestion control is a recent example that will completely no drops, so you can push the AQM to really high drop rate, which will lower the efficiency of the link. So that's
some drawback to that. I don't like most of these things. In most cases, the benefits outweigh the drawbacks, but it's not like we have the oracle we were talking about initially.
Yeah. And of course, if you have the Wi-Fi specific optimization, like in the paper, and of course, then it's specific for that particular technology.
Yes.
So you cannot
Yeah.
necessarily generalize the approach.
No,
Maybe the basis of it.
Yeah, that's why the layer 8 political layer problem is a because we need this in all the bottlenecks. We are over the last 5-10 years with the sort of that was the HUM group in IETF, there was the Bufferbloat project have been banging on doors. There's a lot more awareness now. You see sort of patches going by on the Linux list and people like, no, you will add more Bufferbloat. So that's like the awareness has helped a lot, but there's still a lot of engineering and deployment to get this. So I think mathematics is also the sort of likened it to when you cut down a tree, it has started falling, but it's going to take a while for it to land. But it's falling in the right direction.
Yeah. We move on to here.
Okay. You colleagues have now taken some of my questions away because I did want to ask about the relationship between active coding and simply installing on the blockchain view. But it lets me hammer on coding still a bit more. Because I wasn't set on doing that. Let me try and do that. In FQ coding, what is really the kind of coding?
Yeah. Getting a bit better inflow latency.
Right, who cares about that?
Apparently some people do.
No, I mean specifically. What types of flows care about that?
Yeah, so flows that are TCP based or have some kind of like elastic flows that still want low latency.
Elastic flows that are TCP based on
like
low
equivalent
latency.
like things where you want to discover the like you want to utilize the full link and sort of approach for bandwidth, but you still want low latency.
So can we be more concrete? What kind of application is that? Give me any application example that's going to benefit from the CODL bit in FQ CODL. Because I have problems with that.
I do too. So like you can implement things this way, but you equivalently, if you have something like FQ CODL, you could like if you have a video streaming application that interleaves control.
Right. That runs over UDP often.
Like Netflix things.
Okay, that's one way where you don't care much about the latency. Really.
Yeah, so
a little bit, because you may want to move.
Yes, no, I tend to agree with you that.
Because the biggest issue in my opinion is web traffic. Like for web traffic, just giving it a huge queue makes the chance bigger that all these bursts and slow start basically pass and maybe the traffic is over. So you may end up with faster completion time by buffering a lot. You're not benefiting at all by keeping the queue very small, I think, or simply scale off the one backflow. Right, you're benefiting altogether by just blowing out harming damage, which is what that queue does with this nice fast flow.
But you cannot need infinite buffers in the generator for that to work, right? Like one benefit you get from CODL is that you smooth things out. You have to drop eventually.
Sure, at some point. Yeah. The chances are bigger that the small flow succeeds by when you give it a huge queue. And in web surfing, why does that hurt?
Yeah.
So that will be an example of something where I care about latency, but I care about low completion. Right? And other things like where I care about latency, they often don't send very much. You may have signaling in the game, or you may have one way, or you have dash type traffic, which is again bursts, where you can accommodate them basically. Or you have interactive traffic, which is UDP and tries to often react on queuing behavior. So I'm beginning to suspect that FQ minus cotton is really the best mechanism out there.
But if you have enough buffer.
The more the better.
Yeah. Well,
I got you to say yes. That was a mystery. I said the more the better. You said yeah.
Yeah, sure. As long as you manage it properly. No, but like it goes back to vacuum, right? Like
Yeah.
buffering in itself has value. You just need to manage it.
Okay.
Which is also the reason why just having a small P doesn't help in itself.
Right. Yeah. I have a silly question about FQ public. A very silly one, and it may be something I missed in the papers. Probably I did. But I was just wondering. I mean, first of all, this is also a bit silly in that even the idea of doing this kind of it's a security thing. And I think this kind of attack is by itself silly because FQ public often probably is in my host. Or it may be on a shared network, but just in principle, is that something I could easily attack by creating new flows for every packet?
No, because you will.
But the sparse flow thing is going to.
Yeah, but at some point you're going to go over the threshold. Like you could. There's this thing where flow goes in, it's sparse, it empties out, and then you put it on the normal round-robin rotation before you clear the state. And if you don't do that, then you can have, if you time packets so that they get priority just at the right time, you could have lockout.
Yes.
But now you would just fall back to FQ.
Okay, and also the curiosity probably.
I think we added that in the RFC. You really need to, like, this part is important.
Yeah.
Because,
So now is this going circular, right?
Yes, sir. Round robin.
Yes.
Going back.
So let me go to the Wi-Fi. Maybe I missed that, but your implementation is on the AP access point. And do you deal with the fairness between uplink and downlink?
To a certain extent. So, yes. In the general case, we can't, obviously, because you don't control clients. Yeah. But it turns out because by accounting the RX traffic, the AP will also, when it receives a packet, will either measure or calculate how much airtime that packet take up, and it will account this to that station. So that if the station sends a lot of traffic, its deficit will go down and will be throttled. And if it's a UDP stream, this doesn't do anything. But if it's TCP, that means that the axe will get throttled.
So it throttles on the return channel to
and that, like, it turns out it works pretty well for TCP flows, but it's not a general enforcement mechanism.
Yeah, but because the DCF gives equal number of opportunities to, and the AP is just a station on the network, right?
Yes. So
isn't that the biggest performance anomaly that you could have? Because the AP serves all the other clients, and they serve it in the uplink only themselves. So you get 1/n of the capacity each, and the AP has 1/n of the capacity for the whole down.
Yes. If everyone was just transmitting to one another, that would be true. But like, because most traffic goes through the AP, and because there's like a request response, either TCP or some other component to it, in practice, stations won't keep that. But like, if you just have all stations just blasting UDP out, then you obviously have to.
We have a lot of video streaming from mobile clients and so forth.
Yes.
The downlink would be started.
Yeah. So I at some point I was talking to someone who was doing an application like that, who were having some trouble with this.
Have you considered doing something on the client side or station side to address the deficit round robin could perhaps work also on that side?
Yeah, so but you need coordination. And I'm not sure it would be Wi-Fi anymore.
like there has been some other schemes about this where you like cooperatively, like one of the ways to solve the performance anomaly is you scale your transmission size. You can do that by scaling the aggregate size, and that works really well. But the problem is you can't enforce it, so that comes like it becomes a game theory thing, right? Suddenly you have a incentive to not play nice as a station because you can just grab more items. And I don't think that's really a way. It's like in some respect it's amazing that Wi-Fi works at all because it's like unlicensed spectrum and anyone can transmit anything they want. But it sort of turns out that it works.
So maybe this solution would work.
Yeah, I guess there's definitely some. I'm not an RF guy, but I've heard people talking about their solutions for this at the RF space and the whole way we do spectrum licensing and everything is completely wrong, and we should just have cooperating stations who manage this themselves. But I can't go into the details.
Would it be detectable on the AP side because then the AP could just disassociate its behavior?
Yeah, you can detect it, sure.
Yeah. So then it would just be the AP that would force it simply by cutting off the system.
Yeah, you can still transmit.
Will not be
You can still send RF, right? Like if you,
but then it becomes a jam.
Yeah.
Okay.
Okay, I think quite well covered here from my part of the high level questions, but then I have one question on the paper one related to the conclusions that the paper makes on the data set, this data set. You are using the RPT span as one of the major metrics there.
Yes.
And then in the early part of the paper, you have, or the paper kind of says that the baseline link utilization becomes less important and you can use just the RPT span and you can more or less forget about the mean RPT. But is this really true if you later on the paper makes a conclusion like that if you see delay variation for external delay around 200 milliseconds or more, does that necessarily mean that you
Not necessarily, no.
or is there some cases where that actually is appropriate?
So there's we tried to be fairly careful about how strong claims we made in that paper. Like we're not making the claim that all the RTTs band we say is but definitely not. There can be lots of reasons like variance in paths and variance in transmission delay and all these kind of things. But so the base of the argument is that because it's within one flow and the flow is only 10 seconds long, so you don't get huge, like generally we don't think you get like huge reroutes and suddenly the traffic goes by Japan or something. So it's sort of a stable path-ish. And the minimum RTT on that path is sort of an existence proof that this path has a baseline delay no longer than this because we've seen that we could achieve this RTT. So anything above that is in some way doesn't have to be done.
Always?
No, not always.
Can you give an example when it's not true?
If you have batching serialization, varying in serialization delay or something like the thing you mentioned just before, where you don't get a transmission opportunity until you have a certain number of packets, that sort of thing.
But how about something more simple? You have there bottom link that has, for example, round trip time, polygraph time is 200 milliseconds. If you now see external delay worth of 200 milliseconds, is that external or necessary?
Like if you have a link that's 200 milliseconds.
Yeah, on your part, your proponent link has, or the entire part has something with more than 200 milliseconds round trip delay, but this proponent link has 200 milliseconds. And then you see external delay around 200 milliseconds. Is that the
then you wouldn't get a minimum RTT.
Your minimum RTT is 200 milliseconds, of course, because or something with more than
Yeah, you mean like the magnitude is different compared to the baseline delay? Like,
No, your baseline delay for the mean RTD that you see is 200 around 200 milliseconds. And then you see your span is something like 200.
yeah, so it goes
So
to
doesn't
200.
mean that you have a buffer bloat.
Well, it doesn't necessarily mean you have bufferbloat, but you still have 200 milliseconds of delay that was not
But is that unnecessary?
doesn't have to be, but why would you then suddenly go from 200 to
You know, one TCP plot. How much buffering you need if you have such a single TCP plot? How much buffering you need for that to fully utilize the link?
Yeah, okay.
That's 200 milliseconds, right?
Yes, okay, in that sense.
Okay. So in that sense, what I would like to see is also this some sort of a metric that takes the mean RTP into account, puts it into a classifier from 0 to 20 milliseconds, 20 to 40, and then showing that sense. But yeah, because that would have bring much more information about the possible.
You mean bin it by baseline? Yeah. Sure.
Okay. It's one detail on the one paper.
Yeah.
Okay. I had one question about the BQL thing. I noticed that the data arrives at a value of 6 milliseconds. Whenever I see as configured ideal value.
For BQL?
Yeah.
Which one?
Well, I mean, what is it called?
The THQ thing?
Sorry, yeah, TSQ.
Okay, right. I'm with you.
Right to limits. Yes, I mean, yes, TSQ. So, can you imagine situations where it would be better to be adaptive, to have an algorithm that changes that value dynamically depending on incoming loads, outgoing loads, things like that? It will always be an ideal.
Probably, but the question is if it's worth it, the complexity to doing something like that. So, in the Wi-Fi case, you could adapt it to the actual size of the aggregates that you're sending up. But it's difficult to do because you're still the kernel still sits above quite a bit of logic and firmware and all these kinds of things. So I don't think actually the patch that went into the kernel is not even 6 because it's power 2 pitch.
Yes, yes.
So I think we ended up with 8. And then someone came along and said, our single flow throughput drop, can we increase it to 16?
Yeah.
And we have to put back on that. So you could probably do a lot with, you could try to tune it automatically, but I'm not sure it would be worth the complexity of the processing time and so on. Really simple.
I agree with that, but seriously.
Yeah, we haven't tried. So
all right.
Okay. Yeah, let me take a comment. In your analysis of the Q2 code, you calculated the number of sparse flows. And then you say, so long as an operator is using 8, to calculate the maximum number of sparse flows that it can support, you can be confident that sparse flows are But who knows how many flows there are, and how he forces. Who is she who can say that there shouldn't be more than n flows right now? Right?
Yes.
So how do you think about the whole concept and analysis of getting a number which is emergent in the network, but you cannot control?
Yeah. So this you can control it by doing admission control. And I think some of the Roberts things you were referring to asked this as well, right? So you could add an ingress admission thing that says, I want to guarantee a minimum performance for somebody in a managed network. And that would be basically, in this case, it's more sort of
background and envelope thing, or saying something. Okay, I have the gigabit link in my network. Can I send 100 byte first to it? Sure, go ahead. But you're right. In the general case, that. But in like, yeah.
Because without it, you don't really know where you lie on an operational network. You don't know if you lie. Where this priority effect actually is
yeah. No, but you could use it to figure out when do you need to add more, like when you need to add another link. Oh, I have 200 byte customers. Maybe I should have more. That sort of thing. To sort of inform decisions that you're making. You could also just measure it. And so, oh, my delay starts going up. Maybe I should have another link. That's what people do in practice, right? Sometimes they say, oh, my delay is going up, but I don't want to have another link because.
Okay. Okay, this question is maybe a set of series of questions is related to the way of doing performance measurement analysis and about the results. So the ideal case is of course that you run the measurements and you get the metrics and then you do the analysis and you find out some observe some phenomena there and then you give the not only the results but also the explanation why it's right. And it's not always possible and this should be convincing of course as well. It's not always possible to be 100% sure that this really was the reason. And in that case, like in many of these papers, there are every year and there it says is likely to be the reason. So there's enough or some data to back up this. But when you hear some explanation so that you attribute that this is the reason, then you are quite convinced.
Yes.
Okay. So
Usually.
Okay, if we could take one example.
Yes.
Well, so if you take the paper 2 and the page is 64 to 67, it's maybe helpful if you can look at page 66, where it attributes that before there was this phenomenon that the single TCP connection is causing less external delay than this RRUL test. And the reason for that is kind of it's given in the paper is that the SIN losses are the reason for this. How convinced you are that this is the reason? In the section 5.3.1 and the third paragraph. Well, there are certainly some metrics and the basis to figure this out, and I didn't look at that, but I'm looking at the other results as well, and it became a little bit suspicious. But
so this is a few years back, so I can't remember. I think this is sort of this was the best explanation we could come up with at the time. I don't remember. Maybe we looked at the package traces and saw that we had some similar.
Okay, let me help you a bit. So if you go 2 pages back and take the previous test where it was this void test, and now if you compare the figure 3E and 3F, where you have the same combination, one stream and the RRU, so the flow background. I believe if you look at the people there, you can see the same outcome. So the one stream counts more than the
so ENF?
ENF, yes. So one stream compared with the full RRU. And now, because this is sort of void, there are no SYN segments, I believe, and no SYN losses. So might there be some other reason, maybe which is causing this difference, both here as well as with the webcast? Could this be something?
So you could have, if you have a single flow, it will build up to a full queue, and then we'll get drops, and then we'll drop down a lot. Whereas, yeah. Whereas with all flows, this will not necessarily synchronize. So you would get.
But still the four flows should kind of fill up the queue, so it's delay that you do it doesn't matter whether it's four TCP packets from four flows or one flow, as long as it's or whatever is the level of the queue.
Yeah.
Okay, but there you actually touching that in your answer. So in what the paper is saying that that in your R you just have like right, but and they are kind of taking shorter time. But then if you look at the setup, you have the same.
Yeah. Okay, now I think of it. Yeah, so you have if you have 1,000 packet queue, then half of them are 1,500 bytes and half of them are minimum-sized stacks. Then that takes longer than most of them.
Right, because the queues are specified as packets, not bytes.
Yeah.
And you have majority of the packets there with the arguments are acknowledged.
Yeah, so the reason I'm not sure how we call that to SYN losses. So
because the secret round trip time is much higher with the double or three times.
It relates to the SYN loss in the sense that because it's a 1 megabit link, a single packet takes more than a millisecond.
I'm not saying that the SYN losses are not present. That's part of the reason, but I believe it's not the major. Because you will see, you probably will see SYN losses, but you will see also curious RTOs for SYNs, because in the case of one stream, your actual round trip time is with a full queue is something like 1.6 seconds, and the initial RTO is 1 second. So all your SYNs, if the queue is full, nearly full, we'll see in the one stream case, you'll see curious RTO as well. And it may have the effect as
well. But isn't the RTO for SYNs generally higher than Linux?
And I don't recall what is for Linux, but I recall it is 1 second for Linux as well. Okay, so that is not.
I don't remember the details of why we specifically said the SYN losses.
Okay, but you just to say that when one is kind of the reason one should be quite confident in doing that. So,
yeah, sure. Okay. We spend a lot of time.
I know this is hard. I'm not trying to say that this is some sort of a big shortcoming, but this happens every now and then. But this is why it is research and doing the measurement analysis is really hard sometimes. Especially when we have all the different potential.
Yeah, and like in many we've had a lot of instances of this as well, where we have been scratching our heads for why does this happen, and then maybe it's this, and then we go and change something, and then it turns out like
that's a new topic.
Yeah.
Okay.
Okay. Yes, having prepared for on my role in this committee and getting to my last one, which is similar to what I asked before about cake. I wonder the cake that we can make more effective, specifically the shaping. Or if that would be worth doing. But it could be done, yes. But would it be worth
There's
doing?
Actually, it exists in the form of a product. What is it called? The edge router event something, where they run a daemon that will periodically turn off the shaping, run a test, and then retune the shaping.
Oh, okay.
But
So
it's
you
not
would
built
turn-
into the algorithm. It's just sort of a.
So it would be turned on based on what?
I'm not quite sure how that mechanism works, but the manual tuning we do when we set the rate is that you run a test, measure the delay, then you shape it less and see if that help in the delay. In principle, also.
Exactly. That's what that is what I had in mind. As the delay starts growing, you will start shaping, and you will occasionally stop doing that to see if the volume is shifted.
Yes, that exists. I think even routers they ship open word based routers and have it, but unfortunately it's not open source. Okay, that's secret source. So some people have done this, and it could definitely. And you can also dynamically reconfigure the benefits of that. Just like some experiments doing packet pair kind of thing where you do passive measurements. Captain Mitchell have this tool that could do this. You could conceivably run something on top of it. You would need to occasionally ramp up to see if there's unused bandwidth, but you could at least monitor, oh no, the bandwidth dropped, I need to drop the shape. Right. It would be harder to do for something like Wi-Fi where it happens every 20 seconds. But,
Yes,
but for like a DSL line or something that could.
Yeah. So you could have user space code that would be just adjusting that parameter.
Yeah.
Yeah, that is all I have a question.
Okay, thank you. Gunnar and Martin.
Yeah, I need this anyway, guys. Drop back a bit.
Yeah, okay, one last question. Now, once the thesis is now more done, so and it's time to look at the future. Believe, what would you, if only possible, that you would get one piece of information as a for a AGM designer, I think you can put yourself quite easily to the position of AGM designer. So in the future, if you would have an Oracle system in the sense that there is one additional piece of information that you would have when designing the AQM system, what would that be? That would be helpful. I mean, not necessarily today possible, but it might be someday, just because being Oracle. What metric or piece of information you feel that would help to design the AQM or better AQM? I mean, the AQM systems that we have discussed today, they are not necessarily perfect.
Yeah,
we agree on that.
Some way, I'm going to go look at you now. There's some way for the application to have some kind of API where it could express its intentions of what kind of transport service it wants. Which could then magically be communicated, like an evil bit type of thing in the packet that goes on, and like diff serve that works.
How about the, if you would know the article?
Probably.
I believe the problem one with the concept was, for example, it's the problem.
It would be nice if you, like,
did you say that because it's an evil bit?
That's a different name, but it's a different name, but that's evil.
Like if the sender knew the RTT from the beginning of the flow, that would also be easier to paste things.
Yeah, but who knows the RTT? That's the problem.
Yeah, the Oracle.
Yeah,
you did say
yeah,
like
you
what's
are
about
right? Yeah, exactly. Yeah. But that is the major problem with how we get this information. If we have this information, that might be useful. Of course, there are maybe some other things. Okay, but
Thank you very much to the committee. Now, before we ask all auditorium, also the proxy committee member has a chance to ask questions.
Yes, but it's inspired by the committee. So I wonder if you would turn in a non-sparse flow into semi-sparse flows, what would be the result? Have you measured that? I mean, I guess you wouldn't benefit from it, but how what would the result be? Could you do some experiments and have you done it, or could you measure it somehow?
Well, depends on what you want to achieve.
You can't achieve the reduced latency, I guess. Or,
No.
but
Well,
what would be, I mean, the result if you attempt to do it?
Well, you could get twice. You could get twice the rate and still get priority along with everything else. But at some point, you would run into the capacity, and you would get back to being just an round robin scheduler. So it goes back to a little bit with Michael's question about the security issue with FQCall. Like you can, if you time your packets just right, you can get 1,000 packets that's 1,000 queues. You could send 1,000 packets that would all get priority, but no more. So it's sort of a temporary thing. But if you have a short message that you wanted to send, which just happens to be 5 packets long, for example, you could send it on 5 tuples and it would get priority too. That might be something you could gain. I'm not sure it would sort of have any significant adverse effect on the network. Send the 5 packets.
So you see no risks of abusing your using.
I don't think you can abuse it worse than you would be able to abuse anything else. Like at some point, a DOS attack is a DOS attack, right? And it's only like you can only, because the scheduler goes back. Like either the link has the extra capacity that it doesn't matter and just goes through, or it's already congested and you would pretty quickly go into round robin scheduler. If you do the same thing in a FIFO queue, send a lot of traffic, and they would just take out that queue, and that would also be bad. So I don't think it makes it worse. I haven't when we wrote the RFC, we thought a lot about is this a situation? We couldn't come up with anything that would be worse than it would with a FIFO queue.
And nobody else.
No, not that I know.
Not yet.
It went through the whole ICF process, so I have to think someone probably. Yeah.
Okay, thank you. So now, anybody else has the chance to ask questions? Jonas?
I have 2 short questions. First on low speed Wi-Fi. Maybe you touched this before, but do you think that the queue is the correct place to implement your fairness, or should it be on another layer? Do you fix it on the wrong place, or do you fix it at the correct place? You understand my question?
Yeah. It would probably, yeah. So if we could integrate it directly into the logic that decides which station to send to.
The MAC layer, you mean?
Yeah.
Yeah.
But we can't, because that's in hardware firmware. So it's sort of this is what we could do. But there's a trade-off here. If you implement that into the hardware, and then it turns out down the road that you need to change it, and suddenly you're stuck. So there's also some benefits to doing it at a layer where you can do it. But I think I would rather have sort of help from the hardware, like give me more information. Like Dave Todd has this thing, can I get an interrupt that says, I am done transmitting in 1 millisecond, please send me more data. And you would be able to lower things even more.
Okay, yeah. And second short question is about ludicrous speed. When you saw the graph, you kind of quickly brushed over the speed difference between XTP and DPDK. That it was not so much, but if you look at the figure, it is quite a lot if you look in percentage.
Yes.
But is XTP good enough for the current situation? Can you sustain 100 gigabit? on reasonably sized hardware, or is it at the point where you, yeah, it's a good concept, but we can't use it because it's too slow?
Yeah, so, well, the whole premise is yes, it's good enough. So I'm glad you said yes.
Yeah, because there's quite a lot of difference there, actually.
But if you look at this graph, this one, now we are suddenly higher for another particular case of forwarding and sort of thing. So I don't think you shouldn't see XDP as this is going to to surpass DPDK in raw performance. Like if you just want to send packets as quickly as possible, then probably use DPDK. But if you want more flexibility, if you want to I've heard people express that DPDK is also a really nice way to heat data centers because it will send a CPU that polls the whole time. If you want to have flexibility in that, if you want to do some of the other things, you can get good enough performance for effectively. So if you look at this one, we get to the PCI Express bottleneck before we reach 145 million packets per 100 gig. But absent of that, you can sort of extrapolate that. You just need a few more cores, then you can run 100 gig in theory. So
cores are cheap.
Yeah, just throw more hardware in. But it's definitely going to depend on the use case, like what you want to do. But for many applications, the benefits of XDP will outweigh these relatively small delta performance delta.
Yeah, I agree. It depends on the situation.
This is also we can throw packets away really quickly. Like if you look at the scale of the graph, once you get to something like just forwarding, more than cut performance in half for DPDK as well. Routing, you get down to 5 per core. Like as soon as you start doing more stuff, you will have other issues as well. So I'm not saying that we're going to get parity, but I'm saying that
I don't think parity is really necessary either, as long as you're fast enough.
Yeah, that's what we're trying to get that.
Okay, Andreas?
So I had to ask you this because what is my hobby, and I think we live in very exciting times, right? Because currently we see the industry is having fully programmable hardware at the same cost as fixed function ASICs, and there is P4 and this kind of initiative make queuing, scheduling fully programmable on at terabit speed. So having said that, there's implementation of high Caudal in P4, and Cisco folks are working on that. So what's next? So what is the next cool stuff? You have worked like 5 years on very exciting topics, right? And data center is going to get 100 gig, is already there. So what is the main fundamental, let's say, limitation and challenges in that, like getting to ludicrous speed and having this AQM stuff there? If you have 100 gigs fully programmable hardware, you can record
Yeah, the nice thing about software is its programmability and its flexibility. And if we get that in hardware, that obviously takes away. We don't necessarily need to do it in software. I think my guess is we'll see more hybrid systems. Like you can offload parts of HTTP to hardware as well. You can compile P4 into HTTP or divide stuff out. So there's going to be a lot of exciting things you can do in those systems on top of it. And I think in terms of high-speed processing, HTTP is a building block, and it's really exciting to see what people actually building on top of this. And sort of in terms of future thinking, the other thing is also this very interesting trend, at least currently, that capacity is growing quicker than demand right now. So absent of like next generation application, like maybe adaptive virtual reality or these kinds of things. But with the application, even with like 4K streaming, a gigabit is quite a lot of bandwidth. But that means we can get things like wireless mesh networks, really cheap stuff that will be able to do, that will be good enough that it really you can just throw one up and you can get like citywide mesh networks, these kind of things, because you have spare capacity.
Okay.
Just one question.
Yeah.
So I was wondering, from my understanding, FQCola is basically a mid-range solution. Basically, I mean, you don't. It's very hard to actually have it in the hardware, considering that you have this pair queuing. I'm talking about pair queuing now.
Yeah.
So, what do you think could be a solution for core routers and such? I didn't really understand. Do you have any solution there, or is it the problem in the first place?
Yeah, I think Luca quoted me as saying FQCola is always the answer, and I'm not sure I would. There's like some of the thing I'm missing what the name is. The simulated Spanish string where you have one queue and you keep per flow state will be able to do it. Also shrinking, so you have multiple queues, but not as many, and you do things with those. Could also be a solution. Just in some cases, just plain AQM will at least be better than nothing. And also just like economics, sure, it's really expensive to add lots of transistors to get more queues, but that is also getting cheaper. So I don't think we necessarily need, the technology is there to put stuff in the core as well, in principle.
Okay.
Yes, so a very important question. You know, we had a very hot summer, and there was a question posted on Bloat list recently. I'm not sure if you saw it. Does smart queuing or CODEL contribute to global warming? So someone enabled smart queuing on the router, tempted it with some gun, and it was 5 degrees hotter when they activated the queuing compared to not activating. Yeah. So this touches a bit upon the computational overhead. I mean, we have the $50 router, and you have all these performance comparisons with assumably or presumably unlimited capacity, or not limited. The capacity is not the bottleneck. So how much computational overhead? So it ties up perhaps a little bit into the slide that we are seeing here.
Yeah. So I don't think the example there, it's not necessarily the computational overhead of the algorithm itself compared to doing the same thing. It's the overhead of moving things into software from hardware. So like the main benefit of hardware at the low scales is not like necessarily the maximum capacity, but you can do the same thing with a lower power level. And then you go back into the same, we need smarter hardware. And I think that is mostly a cost thing. You need an ecosystem where you can build devices that are not entirely driven by cost minimization. Someone who actually spends the time to not just take the cheapest module they can find, throw it on the board and ship it for $50. And it is not a technology problem. That's the layout. How do we create demand for better routers? I know of one major ISP that is trying and finding it really hard to get vendors to pay attention, but I think they're succeeding. But to the product you cover, and then we sort of need another product cycle to get it into the hardware.
So it's also a very complex issue, because maybe this 5 degree hotter router would make flows shorter, so you would not have the radio enabled in your cell phone for as long time, which would overall
Yes.
decrease energy. And also this 50 buck router, maybe someone don't have to take their car to work, but if the router would have cost 100 bucks. So I mean, it's a lot of.
Yeah, like the internet is the most complicated machine humanity has ever built. Like this is why it's so fascinating to work with. Like you can always find, if we optimize for this problem and this, and we can do something different. Right?
Thank you.
Okay, any further questions? If not, we should thank again the candidates, the opponent and the committee and the